We have been chasing the wrong planet. For more than half a century, scientists, dreamers, visionaries, and billionaires have pointed at Mars and declared it the next frontier for humanity. Close enough to reach, read enough to inspire poetry, familiar enough to feel like we understand it, but we don't. And the deeper we look at the reality of living there, the clearer one uncomfortable fact becomes. Mars will kill you. Not dramatically, not instantly, but quietly and efficiently. Its atmosphere is thinner than a laboratory vacuum. It has no magnetic field to shield you from cosmic radiation. A single solar storm could cook every colonist on the surface in their own habitat, and yet we keep pretending it's home. Why? Because it's close? Because we've already sent robots? Because admitting we were wrong feels worse than sending humans into a death trap? Meanwhile, 886 million miles beyond Mars, drifting in the cold outer darkness, there is a moon that shouldn't exist. Titan, Saturn's largest satellite, the only moon in the entire solar system with a thick atmosphere, the only world besides Earth where liquids pool on the surface. And according to a growing number of planetary scientists, engineers, and astrobiologists, Titan may be the only place in our solar system where humans could actually survive long-term without burrowing underground like frightened animals. Not just survive, thrive. Walk outside without a pressure suit. Breathe filtered air pulled straight from a nitrogen sky 4 times denser than the one above your head right now. Harvest fuel from methane lakes larger than the Great Lakes. Build a civilization powered by chemistry that has been waiting in the cold for 4.5 billion years. So how did we get it so wrong? And what happens when the best choice for humanity's future isn't the obvious one, but the one nobody saw coming? Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. Mars has been lying to us for more than a century, and we've been eager believers. The 4th planet from the Sun, that rusty red dot in the night sky, has occupied a mythic place in human imagination since the moment we realized it wasn't a wandering star but another world. Giovanni Schiaparelli mapped what he called channels on its surface in 1877. Percival Lowell turned those channels into canals in the 1890s, convinced he was seeing the dying work of a desperate Martian civilization trying to move water from the poles to their drying cities. He was wrong about the canals, wrong about the civilization, wrong about nearly everything except the planet's existence. But the dream he sold never died. It just got more sophisticated. By the time humans started seriously planning to leave Earth, Mars was the obvious choice. It sits right next door on the cosmic block, a mere 55 million kilometers away at its closest approach. Close enough to reach with chemical rockets, close enough that a radio signal takes between 3 and 22 minutes to make the trip depending on where both planets happen to be in their orbits. Close enough that the word neighbour actually means something. It has a 24.5-hour day, nearly identical to ours. It has polar ice caps. It has seasons. It has geology that looks almost familiar to anyone who's spent time hiking through desert canyons on Earth. It has clouds. It has dust storms. It has sunrise and sunset and terrain you could stand on without immediately dying. Compared to Venus, where the surface pressure would crush you flat and the temperature would melt lead, Mars looked downright cozy. Compared to the outer planets, which are just balls of gas with no place to plant a flag, Mars looked solid. Compared to the airless moon, where you'd need a pressure suit just to survive long enough to take 3 steps, Mars looked forgiving. It had an atmosphere, thin but present. It had water, locked in ice but detectable. It had a day-night cycle that wouldn't wreck your circadian rhythm. It checked enough boxes that generations of scientists, engineers, science fiction writers, and billionaires with rocket companies convinced themselves that Mars was humanity's future. The backup drive for civilization, the lifeboat, the second home. They were so eager to believe it that they glossed over the problems. Let's start with the magnetic field, or rather, the complete absence of one. Earth has a powerful magnetic field generated deep in its core where a spinning ocean of molten iron creates electrical currents that wrap the planet in an invisible shield. That shield deflects the solar wind, a constant stream of charged particles blasted out by the sun at speeds of several hundred kilometers per second. Without that magnetic shield, the solar wind would strip away our atmosphere molecule by molecule, irradiate the surface, and turn Earth into something much closer to Mars, which is exactly what happened to Mars about 4 billion years ago. Mars once had a magnetic field. We know this because NASA's MAVEN spacecraft, which has been orbiting Mars since 2014, detected remnant magnetism locked in ancient crustal rocks. Patches of the Martian surface still carry the faint memory of a time when the planet's core churned hot enough to generate its own protective bubble. Then the core cooled. The dynamo stopped. The magnetic field collapsed, and the solar wind got to work. Over billions of years, the Sun stripped Mars bare. What had once been a thicker atmosphere capable of holding liquid water on the surface was peeled away layer by layer, particle by particle, until what remained was a wisp. The surface pressure on Mars today averages about 600 pascals. For context, Earth's surface pressure is just over 100,000 pascals. Mars has less than 1% of the atmospheric pressure we enjoy at sea level. That's not thin air. That's practically no air. It's the kind of pressure you'd find in a laboratory vacuum chamber used to simulate the conditions of low Earth orbit. Here's what that means in practice. If you stood on the surface of Mars without a spacesuit, you wouldn't suffocate first. You'd depressurize. The liquids in your body, your blood, your saliva, the fluid in your eyes would start to boil. Not because Mars is hot. It's not. The average temperature hovers around negative 63 degrees Celsius. But at pressures that low, water boils at body temperature. Your lungs would collapse or rupture depending on whether you tried to hold your breath. You would lose consciousness in about 15 seconds. You would be dead in under 2 minutes, and you wouldn't leave a particularly pretty corpse. The lack of atmosphere means there's no meaningful weather in the sense we understand it. Mars has dust storms, some of them planet-wide, but those storms are driven by temperature differences and the thin carbon dioxide atmosphere responding to seasonal changes in sunlight. They look dramatic in photographs, towering dust devils spinning across ancient riverbeds, but they carry almost no kinetic force. You could stand in the middle of a Martian dust storm and feel nothing more than a gentle breeze. The dust itself is the problem, not the wind. It's fine, abrasive, electrostatically charged, and it gets into everything. Spacesuits, machinery, habitats, lungs if your seal fails. It's not sand. It's closer to powdered glass mixed with toxic perchlorates, chemicals that would sterilize soil and poison anyone unlucky enough to ingest them. Which brings us to the soil. For decades, Mars enthusiasts talked about growing food in Martian regolith, the loose, dusty material that covers the surface. Just add water, they said. Just build a greenhouse, they said. It'll be like the Martian, they said. Except the regolith on Mars is loaded with perchlorate salts, compounds that are used on Earth as rocket fuel oxidizers and industrial chemicals. They're toxic to humans. They disrupt thyroid function. They contaminate water supplies. If you tried to grow a potato in untreated Martian soil, the plant would absorb perchlorates, and you'd poison yourself eating it. You can clean the soil. You can wash it, bake it, treat it chemically. But now you're not farming. You're running a soil remediation operation on an industrial scale before you ever plant a single seed. And you're doing it in an environment where water is scarce, energy is limited, and every resource has to be shipped from Earth or extracted locally at enormous cost. The vision of Martian agriculture as a simple matter of domes and sunlight collapses under the weight of its own logistics. Then there's the radiation. Without a magnetic field and without a thick atmosphere, Mars is a shooting gallery. Cosmic rays, high-energy particles from distant supernovae and active galactic nuclei slam into the Martian surface unimpeded. Solar flares, sudden eruptions of radiation from the sun, wash over the planet with no warning and no protection. The radiation dose on the surface of Mars is about 50 times higher than what you'd receive on Earth. Spend a year on Mars and you'd absorb roughly the same radiation dose as a lifetime on Earth. NASA has a career exposure limit for astronauts, a threshold beyond which the increased cancer risk becomes unacceptable. A single round trip to Mars, 6 months there and 6 months back, would put an astronaut close to that limit before they ever set foot on the surface. Stay on Mars for a year or two, the minimum duration for any realistic mission given the orbital mechanics of getting back, and you'd blow past the limit entirely. You could dig underground. You could pile regolith on top of your habitat for shielding. You could live like a mole and never see the sky except through cameras. But now you're not colonizing a planet. You're hiding from it. Elon Musk talks about 1 million people on Mars by the 2050s. He talks about cities, about terraforming, about making Mars a self-sustaining civilization. He doesn't talk much about the magnetic field he can't build, or the atmosphere he can't hold, or the radiation he can't stop. He talks about rockets, because rockets are the part he knows how to build. The rest is a problem for later, the kind of problem you solve after you've already committed $1 trillion and 10,000 lives to a world that doesn't want you there. Mars is close. Mars is familiar. Mars has ice and rocks and a sky that looks almost like home if you squint. But close doesn't mean habitable. Familiar doesn't mean survivable. The absence of a magnetic field isn't a minor inconvenience. It's a civilizational deal-breaker. It means Mars will never hold a thick atmosphere again without constant artificial replenishment, on a scale that makes every engineering project in human history look like a child stacking blocks. It means the surface will always be a radiation hazard. It means any long-term settlement will be underground, cut off, fragile, entirely dependent on technology that cannot be allowed to fail even once. We spent 100 years pointing at Mars and calling it the future. We built rovers and sent them to drive across its surface. We mapped every crater, every canyon, every dry riverbed. We found water ice at the poles and buried in the regolith. We detected organic molecules, the chemical building blocks that could, in theory, support life. And we convinced ourselves that all of this added up to a place humans could live. It doesn't. Mars is a beautiful, dead, radiation-soaked desert with no air, no magnetic field, and no realistic path to becoming anything else. The closer we look, the clearer that becomes. The data from every probe, every lander, every spectrometer and magnetometer and seismometer we've sent has been telling us the same thing for 20 years. Mars is not the answer. And yet the dream persists, because the alternative is admitting we've been looking in the wrong direction. That the world we thought was close enough and familiar enough to save us is actually a trap. That the real future, the one that doesn't require us to live underground in a radioactive wasteland, lies farther out, in a place so strange, so different, that it forces us to rethink everything we thought we knew about what a second home could look like. Mars fell short because we wanted it to be easy. We wanted the nearest planet to be the right planet. We wanted a world that looked enough like Earth that we could transplant our civilization with minimal adjustment. We wanted to walk outside without a pressure suit, to breathe air that didn't come from a recycler, to see a horizon that felt familiar. Mars offered just enough of that illusion to keep us hooked. But illusions don't build colonies. Physics does, chemistry does, and the physics of Mars are unforgiving. The lack of a magnetosphere isn't something you fix with better technology. It's a fundamental property of a dead planet. The thin atmosphere isn't a temporary setback. It's the endgame of billions of years of atmospheric stripping. The radiation isn't a risk you manage, it's a certainty you endure. Every year we keep pointing at Mars as the destination of choice is a year we're not seriously preparing for the places that might actually work. The momentum behind Mars missions, both governmental and private, is enormous. Billions of dollars in investment, decades of research, entire careers built on the assumption that Mars is step one. And maybe it is. Maybe Mars is a useful waypoint for learning how to live off Earth. A testing ground for the technologies we'll need farther out. But a waypoint is not a destination. A proving ground is not a home. The engineers at SpaceX are brilliant. The scientists at NASA are careful. The entrepreneurs funding private space ventures are ambitious. But none of them can change the fact that Mars lost its magnetic field 4 billion years ago. And without that shield, everything else is compromise. Every habitat is temporary. Every surface structure is a bunker. Every human on Mars is one equipment failure away from death by decompression, freezing, starvation, or radiation poisoning. We built the mythology of Mars on a foundation of optimism and proximity. We convinced ourselves that wanting it badly enough would make it true. We're still doing it. Right now, as you're hearing this, there are teams designing Mars habitats, Mars rovers, Mars rockets. They're solving pieces of an impossible puzzle, making progress on individual problems while ignoring the larger question of whether the puzzle itself is worth completing. Mars isn't going anywhere. It will still be there, red and cold and airless, long after we've stopped pretending it's the answer. But while we've been staring at our closest neighbour, something else has been waiting. Farther out, past the asteroid belt, past Jupiter's radiation-soaked moons, in the soft orange haze of Saturn's orbit, there's a world so strange that it took decades for anyone to take it seriously. A world with an atmosphere thicker than Earth's, with lakes and rivers and rain, with organic chemistry running wild across its surface. A world that shouldn't work as a destination but does. A world that makes Mars look like exactly what it is. A beautiful, dead rock with nothing left to give. We should have been looking at Titan all along. We spent decades staring at Mars, squinting through telescopes, building rovers, mapping every square metre of rust-coloured regolith, trying to convince ourselves it could work. And while we were busy pretending the fourth planet was our destiny, the moon hung there in the sky every single night, closer than anything else in the solar system, taunting us with its proximity, 250,000 miles away, 3 days by Apollo-era rocket. Close enough that 12 human beings walked on its surface between 1969 and 1972 and came home to ticker tape parades. Close enough that we've left flags, footprints, lunar rovers, and bags of human waste scattered across its grey dust. Close enough that we convinced ourselves it was the obvious next step. A lunar base, a lunar colony, a gateway to deeper space. The moon as practice, as infrastructure, as the training ground where we'd learn to live off Earth before tackling the harder stuff farther out. It made sense on paper. It still makes sense if you don't look too closely at what the moon actually is. But the moment you start accounting for the details, the ones that don't show up in artist renderings of gleaming habitats perched on crater rims, the whole idea starts to crack. The moon betrayed us, not because it promised something and failed to deliver. It never promised anything. We just assumed proximity meant suitability, that nearness was the same as habitability, that a place we could reach in 3 days must be a place we could live. We were wrong. The moon is a corpse. It has been dead for billions of years, and unlike Mars, which at least had the decency to die slowly, the moon never lived at all. Start with the atmosphere, or the complete absence of one. Mars has a thin wisp of carbon dioxide that at least registers as an atmosphere, even if it's too thin to breathe or block radiation. The moon has nothing. Not a thin atmosphere. Not a trace atmosphere. Nothing. The surface pressure on the moon is about 3 times 10 to the negative 15 atmospheres. That's not a measurement anyone bothers to make under normal circumstances, because it's effectively indistinguishable from the vacuum of space itself. For all practical purposes, the lunar surface is space, hard vacuum. The kind of environment where water doesn't just boil, it sublimates instantly, transitioning directly from solid ice to vapor without bothering to stop at liquid. Stand on the moon without a spacesuit and the same thing happens to you that happens on Mars, only faster. Your body would attempt to equalize pressure with the surrounding void. The air in your lungs would expand violently. The moisture on your tongue, in your eyes, on the surface of your skin, would flash into vapor. You'd lose consciousness in about 15 seconds, same as Mars, but without even the ghost of an atmosphere to slow the process. You'd be dead in 90 seconds, maybe less. The moon doesn't give you time to regret your mistakes. That vacuum means no weather, no wind, no rain, no erosion in the way we understand it on Earth. The only thing shaping the lunar surface for the last 3 billion years has been impacts. Meteorites, micrometeorites, cosmic dust slamming into the ground at orbital velocities with nothing to slow them down. Over billions of years, that bombardment has pulverized the surface into a fine grey powder called regolith. It covers everything. It's not sand, it's not dirt, it's closer to powdered glass, sharp-edged fragments that haven't been rounded by water or wind because there's never been water or wind to do the rounding. The Apollo astronauts hated it. It clung to everything. Static electricity from the vacuum environment made it stick to their suits, their gloves, their visors. They tracked it into the lunar module after every moonwalk and it smelled, which nobody expected. Regolith exposed to vacuum doesn't have a smell in the usual sense, but once it's brought into a pressurized environment with oxygen, it reacts. The astronauts described it as smelling like spent gunpowder, like burnt metal, acrid and unpleasant. That smell was the regolith oxidizing in the presence of breathable air, a reminder that every particle of lunar dust is chemically reactive in ways Earth dirt isn't. Worse, it's abrasive. The sharp edges wore through the outer layers of spacesuits. Engineers had to design suits with enough redundancy to survive multiple moonwalks because the regolith would slowly grind through fabric, through seals, through anything it touched. Bring that dust into a habitat and it gets into machinery, into air filters, into lungs. It's not toxic in the way Martian perchlorates are, but it's mechanically hazardous. Breathe it and you're inhaling microscopic glass shards. Long-term exposure would shred lung tissue, cause silicosis-like damage, maybe worse. The Apollo astronauts were only on the surface for a few days. Imagine living there. Imagine every time you come back inside, you're dragging invisible razor blades into your air supply. Then there's the radiation. Without an atmosphere and without a magnetic field, the moon is completely unshielded. Earth has both. Our thick atmosphere absorbs or deflects a huge portion of incoming cosmic radiation. What gets through runs into our magnetosphere, the invisible bubble generated by our planet's churning core, and gets channeled away toward the poles where it creates the auroras. The moon has neither. No air, no magnetic field. Just rock and vacuum and nothing between the surface and the rest of the universe. Cosmic rays hit the lunar surface at full strength. These aren't light particles. They're high-energy protons, alpha particles, heavier atomic nuclei moving at a significant fraction of the speed of light. When they hit, they smash into atoms in the rock, creating secondary radiation, a cascade of particles that spreads out from each impact point. Walk on the surface of the moon, and you're standing in a constant invisible hailstorm of particles that will pass through your body, through your spacesuit, through your habitat walls, breaking chemical bonds, ionizing atoms, damaging DNA. NASA measured the radiation dose during the Apollo missions. The astronauts were exposed to about 1 millirem per hour on the lunar surface. That doesn't sound like much until you add it up. A typical chest X-ray gives you about 10 millirems. Spend a week on the moon, and you've absorbed roughly the equivalent of 17 chest X-rays. Spend a year and you're looking at close to 9,000 millirems, roughly 9 rems, enough to measurably increase cancer risk. And that's under normal conditions. A solar flare, a sudden eruption from the sun, could dump 10 to 20 rems in a matter of hours. The Apollo astronauts were lucky. No major solar events occurred during their missions. A future lunar crew might not be. The solution, everyone says, is to go underground. Dig into the regolith, pile meters of rock over your habitat, use the mass of the moon itself as shielding. It works in principle. Cosmic rays lose energy as they pass through matter. Bury yourself deep enough and you can cut your radiation dose to something closer to Earth normal. Lava tubes, ancient underground channels carved out by flowing molten rock billions of years ago, offer natural shelter. Some of them are enormous, large enough to fit entire cities with roofs thick enough to block most radiation without any additional construction. Fine, bury your base, live in a lava tube, problem solved, except now you're living underground, permanently. No windows, no natural light, no stepping outside for a walk, no horizon to look at, no sky, no stars unless you pipe them in through cameras. The psychological research on isolation and confinement is not encouraging. Submariners, Antarctic winter over crews, people who spend months in confined spaces with the same small group of people, show measurable increases in stress, depression, interpersonal conflict, and those environments, as isolated as they are, still have weather, still have external cues, still have the knowledge that they can leave if something goes catastrophically wrong. A lunar base wouldn't have that. You're trapped until the next launch window. If something breaks, if your life support starts failing, if the psychological strain becomes unbearable, you don't get to call for an evacuation. You wait. 3 days if Earth has a rocket ready to go, which it won't. Weeks, or months more realistically. Living underground on the moon isn't like living in a basement, it's like living in a bunker under siege, where the enemy is physics and the siege never ends. And then there's the temperature. The moon's day-night cycle lasts about 29 Earth days. 2 weeks of continuous sunlight, 2 weeks of continuous darkness. During the lunar day, surface temperatures in direct sunlight can climb to around 120 degrees Celsius, hot enough to boil water if there were any water to boil. During the lunar night, temperatures plunge to negative 130 degrees Celsius, cold enough to freeze carbon dioxide into dry ice. That's a 250-degree swing from day to night. No atmosphere means no thermal buffering, no gradual transition, just blazing heat or freezing cold with nothing in between. Any surface structure has to survive both extremes. Solar panels work great during the day, they're useless at night. Batteries can store power, but running a habitat for 2 weeks on stored energy requires massive battery banks, heavy equipment you'd have to ship from Earth or manufacture locally using resources you don't have yet. radioisotope thermoelectric generators, nuclear power sources that produce heat from radioactive decay, can provide steady power regardless of sunlight, but they're expensive, politically complicated, and produce only modest amounts of electricity compared to solar arrays. The poles offer a partial solution. The Moon's axis is tilted only about 1.5 degrees, far less than Earth's 23.5-degree tilt, which means there are places near the lunar poles where the terrain is high enough to catch near-continuous sunlight. Peaks of eternal light, they're called, mountaintops that almost never see darkness. These regions are scientifically interesting and practically useful. Set up solar panels there and you have near-constant power. Build a base nearby and you avoid the worst of the temperature swings. NASA and other space agencies have been eyeing the lunar South Pole for exactly this reason. The catch is that these regions are small, highly specific, and geographically constrained. Everyone going to the Moon is going to want the same real estate. That's fine for a single base, maybe two. Scale it up to a colony, to permanent infrastructure, to anything resembling long-term settlement, and you run out of optimal locations fast. You're forced to expand into less favourable terrain, back into the regions with 2-week nights and temperature swings and all the problems that come with them. Water helps, at least in theory. We've known since the late 1990s that there's water ice on the Moon, concentrated in permanently shadowed craters near the poles where sunlight never reaches, and temperatures stay low enough to trap volatile compounds for billions of years. NASA's LCROSS mission in 2009 deliberately crashed a spent rocket stage into one of these craters and measured the debris plume. They found water, not a lot, but enough to confirm the stuff is there. Subsequent missions, orbiters with sensitive spectrometers, have mapped the distribution in more detail. The ice is real, it's accessible, it's a resource. Except accessing it is harder than it sounds. The permanently shadowed craters are cold, -200 degrees Celsius or lower, darker than any night on Earth, and filled with the same abrasive regolith that covers the rest of the Moon. Mining ice from these craters means working in the coldest, darkest, most hostile environment the Moon has to offer. You need power, you need heat, you need machinery that can survive operating in temperatures where most metals become brittle and most lubricants freeze solid. You need to transport the ice, process it, break it down into hydrogen and oxygen for fuel and life support, all while dealing with equipment that's constantly getting clogged with dust and irradiated by cosmic rays. It's doable. We have the technology. But doable and practical are not the same thing. Every kilogram of water you extract from a lunar crater costs energy, equipment, time, and risk. For a small base, maybe it's worth it. For a colony, for thousands of people, the amount of infrastructure required to make lunar water extraction viable at scale starts to rival the cost of just shipping water from Earth, which defeats the entire point of using local resources in the first place. The Moon has been sold as a stepping stone, a place to test technologies, to learn how to build habitats, to practice living off-world before committing to Mars or somewhere farther out. That narrative isn't entirely wrong. There are things we can learn on the Moon that we can't learn anywhere else. How to construct in vacuum, how to manage radiation exposure, how to maintain machinery in abrasive dust, how to grow food under artificial light with no atmosphere and minimal gravity. These are useful skills. They translate to other environments, but calling the Moon a stepping stone implies that it's part of a path, that success there leads naturally to success elsewhere. And that's where the analogy falls apart. The Moon is not a practice version of Mars or Titan or anywhere else. It's its own set of problems, most of which don't exist in the same form on other worlds. Mars has an atmosphere, thin but present. Titan has a thick one. Both have weather, temperature cycles moderated by air, surface conditions that resemble Earth more than the Moon does. Learning to live on the Moon teaches you how to survive vacuum, extreme temperatures, and unshielded radiation. Useful, yes. But it doesn't teach you much about living on a world with weather, with liquid on the surface, with chemistry that might actually support something beyond bare survival. And psychologically, the Moon is brutal. It's close enough to Earth that you can see home in the sky, a blue marble hanging above the horizon, close enough to feel tantalizingly within reach, close enough that the isolation feels worse, not better. You're not exploring the frontier, you're marooned in sight of shore. Astronauts on the International Space Station, in low Earth orbit just 400 kilometers up, report feeling connected to Earth. They can see cities, They can watch weather patterns develop in real time. They're still part of the planet in a way that feels tangible. The moon strips that away. You're 250,000 miles out. Far enough that Earth looks small, far enough that radio signals have a noticeable delay, far enough that rescue is measured in days at best and weeks more realistically. Close enough to see what you left behind. Close enough to feel abandoned. We built the mythology of the moon on proximity and nostalgia, the same way we built the mythology of Mars. We wanted the nearest place to be the right place. We wanted to believe that the first step off Earth would be the easiest, that the closest destination would be the most forgiving. We convinced ourselves that a 3-day trip and 50-year-old boot prints meant the moon was ready for us. That all we had to do was go back, this time to stay. The moon isn't ready. It will never be ready in the way we want it to be. It has no air, no magnetic field, no shelter except what we dig or build, no resources except ice trapped in frozen craters and regolith that cuts through equipment like sandpaper. It's as hostile to human life as any place in the solar system that isn't actively trying to kill you with acid rain or crushing pressure. The only advantage it offers is distance, and distance by itself is not enough. Every proposal for a permanent lunar presence, every plan for a moon base or a lunar gateway or a mining colony comes with pages of assumptions. Assumptions about radiation shielding, about in-situ resource utilization, about closed-loop life support systems that recycle air and water with near-perfect efficiency. Assumptions about human endurance, about psychological resilience, about our ability to live underground in small metal boxes for months or years without breaking. And maybe all of those assumptions are correct. Maybe the engineering challenges are solvable. Maybe we can build a base on the moon that works. But solvable doesn't mean it should be solved. Not when there are alternatives farther out that don't force us to compromise so much just to survive. The moon taught us one thing clearly. Proximity is a lie. The nearest place is not the best place. The world we can reach fastest is not the world we should aim for. And every year we spend trying to make the moon habitable is a year we're not preparing for the places that might actually give us a future. Mars offered familiarity and failed. The moon offered closeness and betrayed us. Both fell short because we kept looking for versions of Earth, for places that felt similar enough that we could transplant our civilization without changing too much. We wanted worlds where the compromises would be small, where the adaptations would be manageable, where we could step outside without immediately dying and call that progress. Those worlds don't exist, not close by, not in the inner solar system. The places we wanted, the ones that matched our expectations and our comfort zones, turned out to be traps, beautiful from a distance, deadly up close. And while we were busy staring at them, measuring them, convincing ourselves they could work, something else was waiting farther out. 886 million miles from the Sun, orbiting Saturn in a thick orange haze, a world so strange that almost no one took it seriously as a destination until the data forced them to. A moon with an atmosphere thicker than Earth's, with lakes and rivers, with weather and seasons, with organic chemistry running wild across a surface we're only just beginning to understand. Titan, the place we should have been looking at all along. We spent 50 years staring at Mars trying to make the math work. We spent another 50 staring at the moon, trying to pretend proximity was the same as suitability. And while we were busy failing at both, the answer was sitting almost 900 million miles away, orbiting Saturn in a cloud of orange haze so thick that for decades we couldn't even see the surface beneath it. A moon larger than the planet Mercury. A moon with an atmosphere. A real one. Not a wisp, not a trace, not a ghost of what used to be. An atmosphere thicker than Earth's. With weather. With rain. With lakes and rivers and coastlines mapped in radar images that shouldn't exist because no other moon in the solar system has anything like them. That moon is Titan. And the reason you've probably never heard anyone talk seriously about colonizing it is that 886 million miles sounds like a deal breaker. It sounds impossible. Mars is 55 million kilometers away at closest approach, close enough that we've convinced ourselves it's reachable despite being utterly hostile to human life. Titan is more than 15 times farther out. At Saturn's distance from the Sun, about 9.5 astronomical units, the sunlight is so dim that solar panels become nearly useless. The round-trip travel time with current propulsion technology would be measured in years, not months, and the psychological weight of that distance, the sheer alienness of a destination that far from home, has kept Titan off the shortlist for human exploration for most of the history of space travel. We looked at the distance and stopped thinking. That was the mistake. Titan has been hiding in plain sight since 1655, when a Dutch astronomer named Christian Huygens spotted a faint point of light near Saturn and realised it was a moon. He called it Luna Saturni, Saturn's moon, because at the time no one had bothered naming these things yet. That job fell to John Herschel almost 2 centuries later, who reached back into Greek mythology and pulled out the name Titan, appropriate given what the place turned out to be. But for most of the time between Huygens' discovery in the late 20th century, Titan was just another dot in a telescope. Bigger than most, sure, interesting in an academic sense, but still just a moon, one of dozens orbiting the outer planets, none of which seemed particularly relevant to anyone not writing astronomy papers. Then, in 1980, Voyager 1 arrived at Saturn. The spacecraft had already flown past Jupiter the year before, sending back images of that planet's cloud bands and its 4 large Galilean moons. Saturn was next on the itinerary, and the mission planners had programmed a close flyby of Titan because it was the biggest target available, and because the instruments might as well look at something interesting while they were out there. Nobody expected what they found. Voyager's cameras saw nothing, or rather, they saw a smooth, featureless orange sphere. No surface detail, no craters, no mountains, nothing but haze. That haze was an atmosphere, and it was enormous. Voyager's instruments measured it extending hundreds of kilometers above the surface, far thicker and more substantial than anything around any other moon in the solar system. The composition analysis came back with nitrogen as the dominant component, about 95%, with methane and trace amounts of other hydrocarbons making up the rest. An atmosphere made primarily of nitrogen, just like Earth's. That should have been the moment Titan became interesting. It was to scientists. To everyone else, it was still just a distant moon with a thick atmosphere and no visible surface. You couldn't see what was down there. The haze blocked everything, and without a visible surface, without features to map and photograph and put on posters, Titan remained abstract. Voyager moved on. The data went into journals, the decades rolled forward, and Titan stayed on the list of places that were scientifically curious but practically irrelevant. The breakthrough came 25 years later, and it didn't come from orbit. It came from the surface. In October 1997, NASA launched the Cassini spacecraft, a car-sized orbiter carrying the most sophisticated suite of instruments ever sent to the outer solar system. Attached to Cassini was a smaller probe called Huygens, built by the European Space Agency and named after the astronomer who discovered Titan. The plan was for Cassini to enter orbit around Saturn, spend years studying the planet and its moons, and at some point detach Huygens and send it plunging through Titan's atmosphere to see what was actually down there. Cassini arrived at Saturn in July 2004 after a 7-year journey. By December, the spacecraft had maneuvered into position, and on Christmas Day, Cassini released Huygens. The probe drifted on a ballistic trajectory toward Titan, unpowered, inert. A metal shell packed with cameras, spectrometers, and a heat shield designed to survive entry into an atmosphere whose exact density was still uncertain. 3 weeks later, on January 14th, 2005, Huygens hit the top of Titan's atmosphere at 6 kilometers per second. For the next 2.5 hours, Huygens fell. The heat shield took the worst of the entry deceleration, slowing the probe to a speed where parachutes could deploy without ripping apart. At about 160 kilometers altitude, the main chute opened, and Huygens began its slow drift downward through the haze. Cameras turned on, instruments started measuring, data streamed back to Cassini overhead, which relayed it to Earth. And for the first time in history, something built by humans was looking at the surface of Titan. The images came back in pieces, blurry at first, resolving as the probe descended. What they showed stopped people cold. The surface wasn't flat. It wasn't a featureless plain. It had hills. It had valleys. It had drainage channels carved into the terrain like river networks on Earth, branching and converging in patterns that screamed liquid erosion. Darker regions that looked like they might be standing bodies of fluid. Brighter highlands, rounded stones scattered across flat plains. Erosion. Weather. geology shaped by processes that required liquid on the surface. Huygens touched down on solid ground, the first and so far only spacecraft to land on a world in the outer solar system, the most distant landing ever. It transmitted data from the surface for about 90 minutes before the cold drained its batteries, and in that hour and a half, every assumption about Titan being just another dead frozen moon collapsed. The surface pressure came back at roughly 1.4 atmospheres, slightly higher than Earth's sea level pressure, not a trace, not a whisper. A real atmosphere pressing down from above with enough weight that a human body wouldn't explosively decompress. The temperature was negative 179 degrees Celsius, cold enough to freeze methane into solid ice and turn water into rock. But the pressure was there. The atmosphere was thick enough to breathe if it weren't made of nitrogen and methane, thick enough to scatter light and create a sky, thick enough to moderate temperature swings in a way that Mars and the Moon could never do, thick enough to protect the surface from the worst of cosmic radiation and micrometeorite bombardment. And the liquid was real, not water, too cold for that. Methane and ethane, hydrocarbons that stay liquid at Titan's surface temperature, flowing through channels, pooling in lakes, evaporating into the atmosphere and condensing into clouds. A hydrological cycle, the same basic process that drives weather on Earth, except running on methane instead of water. Evaporation from the surface, cloud formation, precipitation, rain falling from the sky, hitting the ground, running downhill into rivers and streams that empty into lakes and seas. The same cycle, just shifted to a different chemistry. The radar mapping from Cassini confirmed it over the next decade. Titan has lakes near its poles, hundreds of them, some as large as the Great Lakes in North America. It has seas, bodies of liquid methane and ethane big enough to qualify as oceans if they were on Earth. The largest, Kraken Mare, covers an area bigger than the Caspian Sea. Ligeia Mare, another major sea, has been measured at depths of at least 160 meters. These aren't puddles. They're not temporary features left over from some ancient event. They're active, stable bodies of liquid, fed by rivers, shaped by shorelines, interacting with an atmosphere that cycles their contents into clouds and rain. Titan has weather in the way Earth has weather, with storms and precipitation, and seasonal changes driven by the tilt of Saturn's orbit around the Sun. That shouldn't be possible. No other moon in the solar system does this. Europa has an ocean, but it's buried under kilometers of ice. Enceladus has geysers, but they erupt from a subsurface sea into vacuum. Ganymede is bigger than Titan, but its surface is frozen solid with no atmosphere to speak of. Titan is the only moon with a thick atmosphere, the only moon with liquid on its surface, the only moon where a weather forecast would mean anything. It's not acting like a moon, it's acting like a planet. A cold, alien planet with chemistry that doesn't resemble Earth's in detail, but resembles it in function. A place where fluids move, where energy cycles through the system, where the surface is shaped by processes that require something other than just impacts and radiation, and it's sitting 886 million miles away, which is why no one takes it seriously. That distance isn't just inconvenient. It's a barrier that reshapes every assumption about logistics, mission duration, cost, and human endurance. A trip to Mars with current chemical rockets takes 6 to 9 months. A trip to Titan, even with gravity assist from Jupiter to pick up speed, takes closer to 7 years. Cassini-Huygens took 7 years. New Horizons, which flew past Pluto, took 9 years to reach the outer solar system, and it didn't stop. Any mission to Titan that intends to stay, to land, to establish a presence, is signing up for a travel time measured in the better part of a decade each way. You're not coming home for the holidays. You're not coming home at all, unless you're willing to spend another 7 years in transit on the return leg. A round trip, accounting for mission time on the surface, could easily span 20 years or more. That's half a human lifetime locked into a single journey. The energy requirements are brutal. Getting to Mars requires accelerating to about 5 kilometers per second relative to Earth, then slowing down to match Mars' orbital velocity. Getting to Saturn requires more than 15 kilometers per second, with gravity assists from inner planets if you want to shave years off the trip. The further out you go, the more delta V you need, and delta V costs fuel. Fuel has mass. Mass makes your rocket bigger, which requires more fuel to lift, which makes it bigger still. The tyranny of the rocket equation, the exponential relationship between fuel and payload, hits you harder the further you aim. Mars is barely at the edge of what chemical rockets can do efficiently. Titan is so far beyond that edge that conventional propulsion starts to look absurd. That's why nuclear propulsion keeps coming up in serious mission proposals. Ion drives, nuclear thermal rockets, maybe nuclear pulse propulsion if anyone ever gets comfortable with the idea of detonating small nuclear charges behind a spacecraft to push it forward. Technologies that can sustain thrust over months or years, that don't require carrying enormous tanks of chemical fuel, that make the distances involve something other than a logistical nightmare. None of these systems exist in flight-ready form yet, though NASA and others have been working on prototypes for decades, and none of them make Titan close. They just make it reachable without requiring magic. But here's the part nobody talks about when they dismiss Titan as too far. Once you're there, once you've paid the cost of getting 886 million miles out into the outer solar system, you're somewhere that doesn't punish you for existing. You're not hiding underground from radiation. You're not rationing every breath of air or managing pressure suits every time you step outside. You're standing on a world with a thick atmosphere that provides real protection, real pressure, real buffering against the hostility of space. A world where the engineering challenges shift from survival to comfort, where the baseline isn't dying slowly but living differently. The atmosphere alone changes everything. On Mars, you need a full pressure suit every time you leave a habitat. Hard shell, life support, redundant seals, the works. A suit failure means death in minutes. On the Moon, same problem, vacuum, no air, instant catastrophe if something goes wrong. On Titan, the pressure is higher than Earth's. The air is nitrogen, unbreathable but not toxic. You don't need a pressure suit. You need a breathing mask and heating. That's it. Walk outside in insulated clothing, a respirator feeding you oxygen, and you're fine. The pressure differential between your lungs and the surrounding air is negligible. Your body isn't trying to equalize with vacuum. Your blood isn't boiling. You're just cold and you can't breathe the local air, both of which are solvable with much simpler, much lighter, much cheaper equipment than a full EVA suit. That difference is not minor. It's the difference between needing a spacecraft-grade life support system strapped to your back and needing a parka and a gas mask. It's the difference between every trip outside being a high-risk operation, requiring checklists and buddy systems and backup plans, and every trip outside being routine. The kind of routine where you can build structures, move equipment, expand infrastructure without constantly fighting the environment's attempts to kill you. Titan's atmosphere does half the work of keeping you alive just by existing. Everywhere else in the solar system outside of Earth, the atmosphere is your enemy or it doesn't exist. On Titan, it's an asset. And the distance that makes Titan sound impossible, the 886 million miles that keeps it off the shortlist, is starting to look less like a barrier and more like a filter. A threshold that forces us to think differently, to stop pretending we can colonize the solar system with 1960s technology and contemporary assumptions. Mars is close enough that we keep trying to brute force it with chemical rockets and optimism. Titan is far enough that brute force doesn't work. You have to solve propulsion. You have to solve closed-loop life support for multi-year journeys. You have to solve psychological endurance, crew selection, resource autonomy. And once you've solved those problems, once you've built the infrastructure to reach Titan and survive the trip out, you're not just setting up a base, you're laying the groundwork for deep space exploration on a scale that makes Mars missions look like test flights. The data from Cassini kept piling up for 13 years. The spacecraft orbited Saturn, flew past Titan more than 120 times, mapped the surface in radar, measured the atmospheric composition in detail, tracked seasonal changes, watched storms develop and dissipate, identified hundreds of lakes and seas, traced river networks, spotted mountains, measured wind speeds. Every pass added another piece to the picture. Titan wasn't static. It was dynamic, active, a world with processes running in real time that shaped the surface and cycled material between the ground and the sky. In 2017, Cassini ran out of fuel. NASA chose to end the mission by sending the spacecraft into Saturn's atmosphere rather than risk it crashing into one of the moons and potentially contaminating them with Earth microbes. On September 15th, Cassini fired its thrusters one last time, tipped itself towards Saturn, and burned up in the planet's outer atmosphere, sending data until the signal cut out. The mission was over. The map it left behind was complete enough to answer the big questions about what Titan was, and the answer was clear. Titan wasn't like anywhere else. It had an atmosphere, liquid on the surface, weather, chemistry, geography shaped by forces other than impacts and gravity. It was the only place beyond Earth where a weather report would matter. The only place where you could walk outside without a pressure suit. The only place where the baseline environment wasn't actively trying to kill you every second you stayed there. NASA's already planning the next mission. Dragonfly, a nuclear-powered quadcopter drone the size of a car, scheduled to launch in the late 2020s and arrive at Titan in the mid-2030s. It'll fly from site to site, covering hundreds of kilometers, sampling surface materials, analyzing atmospheric composition, looking for prebiotic chemistry, mapping terrain in detail that Cassini's radar couldn't resolve. A flying robot exploring a moon with an atmosphere thick enough to support rotorcraft. That's not science fiction. That's an approved mission with hardware in development. And if a drone can fly there, if the atmosphere is thick enough to provide lift and stable enough to navigate, then everything about how we think about exploring Titan changes. You're not limited to a single landing site. You're not locked into a rover that crawls across the surface at walking speed. You can move fast, you can cover distance. You can explore in a way that looks less like planetary science and more like aerial survey, hopping between lakes, sampling different terrains, building a map from direct observation rather than orbital inference. That's the Titan nobody talks about. The one that doesn't fit the script of distant, frozen, unreachable. The one that offers something other than bare survival in exchange for the cost of getting there. The one with an atmosphere that does more than exist. That shields, that moderates, that supports weather and liquid and processes we recognize even if the chemistry is alien. The one where the compromises we'd have to make aren't about staying alive in a hostile wasteland, but about adapting to a functional ecosystem running on different rules. 886 million miles, 7 years of travel time, a destination so far from the sun that solar panels barely work and the sky is dim even at midday. A moon orbiting a gas giant in a system so far removed from Earth that radio signals take more than an hour to cross the distance. That's Titan. And underneath all of that distance, underneath the haze and the cold and the alien chemistry, is the only place beyond Earth where you could step outside, look up at a sky, feel an atmosphere pressing down around you, and not immediately die. The only place where walking on the surface doesn't require a spacecraft strapped to your body. The only place where the rain that falls from the clouds actually reaches the ground and flows into rivers. We've been looking for the wrong things in the wrong places. Mars offered familiarity and had nothing underneath. The Moon offered proximity and gave us a dead rock. Titan offers distance, cold, strangeness, everything that should disqualify it. And underneath all of that, it offers an atmosphere, real weather, liquid on the surface, a baseline environment that isn't vacuum or unbreathable poison or radiation-soaked dust. The distance is the price. The atmosphere is what you get for paying it. And the atmosphere, as it turns out, is the one thing everywhere else doesn't have. We've spent centuries assuming that atmosphere was a luxury, something rare, a feature that belonged to planets lucky enough to be the right size, the right distance from their star, with the right combination of gravity and magnetic field to hold onto their air. Earth has one, Venus has one, though it'll crush and melt you. Mars had one and lost it. The Moon never bothered. And everywhere else we've looked in the inner solar system, from Mercury to the asteroid belt, the answer has been the same. No air, no protection, nothing between you and the raw hostility of space, except whatever metal and polymer shell you happen to be wearing or living inside. That assumption shaped everything. It shaped our spacesuits, our habitats, our entire approach to living off Earth. It made us think that leaving our atmosphere meant accepting a permanent state of siege, where every breath requires technology, and every surface exposure requires armor. It made us think atmosphere was the exception, and vacuum was the rule. And for 50 years of space exploration, confined to the inner solar system and low Earth orbit, that assumption held. Every moon we visited was airless. Every rock we landed on had nothing above it but radiation and silence. Then we got to Titan, and the assumption shattered. Titan's atmosphere isn't a wisp. It isn't a remnant. It isn't the fading ghost of something that used to be thicker. It's a fully functional, actively maintained atmospheric system that would make Earth's look anemic if you put them side by side under comparable conditions. The numbers are straightforward and they upend everything. At Titan's surface, the atmospheric pressure is 1.448 times Earth's sea level pressure. Not 90%, not similar, higher. Stand on Titan and the air above you is pressing down with 60% more force than it does in New York or London or Tokyo. That's the pressure you'd feel if you dove about 15 feet underwater on Earth. Noticeable, but not crushing. Comfortable even. The kind of pressure differential that human bodies handle without difficulty every time someone goes swimming. For context, that's not just higher than Mars. Mars has 0.6% of Earth's atmospheric pressure. Titan has 144.8%. You're not comparing similar environments with different details. You're comparing a category that barely exists to a category that exceeds the baseline. Mars is functionally vacuum. Titan is functionally Earth plus. The composition matters as much as the density. Titan's atmosphere is 95% nitrogen, the same element that makes up 78% of Earth's air, not carbon dioxide like Mars or Venus, not methane or ammonia or sulfur compounds or any of the exotic chemistries you find in gas giant atmospheres. Nitrogen. Inert, stable, non-toxic, the background gas that fills your lungs with every breath you take right now without contributing anything to the actual respiration process. On Earth, we breathe nitrogen in and breathe it right back out unchanged. It's filler. The oxygen is what matters. Titan's atmosphere is almost entirely that filler, with about 5% methane and traces of other hydrocarbons mixed in. That methane is flammable, yes. In the presence of oxygen, it would burn, but there's no free oxygen on Titan. The methane just sits there, inert, cycling through the atmosphere as part of the weather system. You can't breathe it, but it won't hurt you by contact. It's not acid. It's not corrosive. It's just a simple hydrocarbon drifting through a nitrogen atmosphere at temperatures so cold that water ice is as hard as granite. What that means in practical terms is that Titan's air is almost exactly the pressure and composition your body expects, minus the oxygen. You could walk outside on Titan wearing insulated clothing and a breathing mask that supplies oxygen, and your body would not notice a pressure difference. No squeeze, no strain, no risk of decompression. Your lungs would expand and contract normally. Your ears wouldn't pop, your sinuses wouldn't ache. You wouldn't feel like you were holding your breath or suffocating or trapped in a coffin. You'd just be breathing bottled air in an environment where the surrounding atmosphere does everything an atmosphere is supposed to do except provide breathable gas. Compare that to Mars. Every time you step outside a Martian habitat, you're suiting up in what amounts to a personal spacecraft. Hard-shell torso, pressurized joints, life support backpack, layers of insulation, radiation shielding if the designers remembered to include it, which they often don't because mass constraints are brutal. The suit is maintaining one full atmosphere of pressure around your body while the outside world sits at 0.006 atmospheres. That's a pressure differential of more than 16 to 1. Your suit is holding back vacuum. One puncture, one failed seal, one torn glove, and you're in immediate life-threatening trouble. The air in your lungs would try to equalize with the outside. Fluids in your body would start to boil. You'd have seconds to get back inside or patch the hole before you lost consciousness. On Titan, you don't need a pressure suit. The atmosphere is already doing the job, you need heat. Titan's surface temperature sits at around negative 179 degrees Celsius, cold enough that exposed skin would freeze in seconds. But cold is a solvable problem. Insulation works. Electric heating works. We've built clothing that keeps humans alive in Antarctica, in the Arctic, in high-altitude environments where temperatures drop well below negative 50 Celsius. Titan is colder, yes, but it's not orders of magnitude colder. It's the same kind of problem, just turned up. You wear a heated suit, well insulated with an oxygen supply feeding a mask or a helmet. The whole setup could weigh a fraction of what a Mars EVA suit weighs, because you're not fighting pressure differentials. You're just staying warm and breathing. That difference cascades. Lower suit mass means easier mobility, less energy expenditure, longer working time outside. Simpler suits mean cheaper production, faster turnaround, more suits available per mission. Fewer points of failure mean lower risk per EVA. And lower risk per EVA means you can treat surface operations as routine, rather than high-stakes events that require extensive pre-breathing protocols and multiple redundant safety checks. On Titan, going outside could be closer to putting on a coat and mask and stepping into cold weather. On Mars, it's closer to preparing for a spacewalk. Then there's the radiation shielding, and this is where Titan's atmosphere stops being a convenience and becomes a legitimate game changer. Cosmic rays. those high-energy particles screaming through space from supernovae and active galactic nuclei and solar flares, lose energy every time they collide with an atom. A thick atmosphere means billions upon billions of atoms between the source of the radiation and the surface. Every collision slows the particle, deflects it, or breaks it apart into secondary particles that themselves collide and lose energy. By the time cosmic rays make it through Titan's atmosphere to the surface, the vast majority of their energy has been absorbed. NASA's assessments of Titan specifically note that the thick atmosphere reduces radiation exposure to negligible levels compared to Mars or the Moon, not lower, negligible. The difference between standing on Mars and standing on Titan in terms of radiation dose is the difference between standing in a hailstorm and standing under a concrete roof. Mars offers no protection. Titan offers the kind of shielding that makes long-term surface exposure survivable, without requiring meters of regolith piled on top of your habitat, or forcing everyone to live underground like refugees. Earth's atmosphere provides similar protection. At sea level, we're shielded from the worst of cosmic radiation by the full column of air above us, roughly 10 tons per square meter of atmospheric mass between the ground and space. Titan's atmospheric mass per unit area is even higher because the atmosphere is denser despite the Moon's lower gravity. The column of air pressing down on Titan's surface is thicker and heavier than Earth's. That thickness is a shield, a passive, always-on, maintenance-free radiation barrier that doesn't require power or replacement parts, or anyone remembering to turn it on. For comparison, Mars has effectively no atmospheric shielding. The thin carbon dioxide atmosphere absorbs a tiny fraction of incoming radiation, but nowhere near enough to matter. Spend a year on Mars and you're absorbing a radiation dose equivalent to multiple CT scans, enough to measurably increase cancer risk and enough to push astronauts past NASA's career exposure limits. Spend a year on Titan, and the radiation dose is a rounding error. The atmosphere is doing what Earth's atmosphere does, just with nitrogen and methane instead of nitrogen and oxygen. That has immediate implications for habitat design. On Mars or the Moon, any structure exposed to the surface is a radiation hazard. You either bury it, pile regolith on the roof, or accept that everyone inside is getting dosed. Long-term habitation requires going underground, living in lava tubes or excavated tunnels, cutting yourself off from natural light and surface access. On Titan, you can build on the surface. You still need insulation against the cold, you still need airtight seals to keep your breathable atmosphere in, and Titan's nitrogen-methane mix out. But you don't need radiation shielding beyond what the atmosphere already provides. Windows become practical. Surface structures become practical. The entire design philosophy shifts from bunker to building, and then there's mobility, which ties directly into Titan's combination of dense atmosphere and low gravity. Titan's surface gravity is about 14% of Earth's, 1/7. If you weigh 70 kilograms on Earth, you'd weigh about 10 kilograms on Titan. Muscle strength doesn't change, mass doesn't change in terms of inertia, but weight, the force pulling you toward the ground, drops dramatically. Walking becomes easier, lifting becomes easier, carrying equipment, moving materials, constructing infrastructure, all of it gets lighter. Now combine that low gravity with an atmosphere that's 50% denser than Earth's. On Earth, air resistance is noticeable when you're moving fast, cycling, driving, running. On Titan, with denser air and lower gravity, that resistance becomes a usable force at much lower speeds. Wings work better, rotors work better. Anything that generates lift by pushing against air becomes absurdly efficient. A human in a lightweight wingsuit could probably glide on Titan with minimal effort. A small electric motor driving a propeller could lift significant weight. Rotorcraft, the kind of quadcopter drones that struggle with payload limits on Earth, become cargo-hauling workhorses on Titan. That's not speculation. NASA is already banking on it. The Dragonfly mission, scheduled to launch in the late 2020s, is a nuclear-powered quadcopter the size of a car. It'll fly from site to site on Titan, covering hundreds of kilometers, landing to take samples, then taking off again. The mission design is built around the fact that Titan's atmosphere makes flying easier than driving. You don't need runways, you don't need roads. You just lift off, fly to where you're going, and land. The dense air provides lift. The low gravity makes the energy cost negligible compared to what the same maneuver would require on Earth. Scale that up to human operations and the implications are hard to overstate. Transport on Titan doesn't look like Mars rovers crawling across the desert at walking speed. It looks like aircraft. Small personal flyers, cargo drones, maybe even manned vehicles that take off vertically, fly at altitude where wind resistance is even lower, and land wherever they're needed. The infrastructure requirements drop compared to building roads or rail. You're not tied to a single base location. You can spread out, explore, establish multiple sites without needing a ground transportation network connecting them. The atmosphere makes all of that possible in a way it isn't anywhere else in the solar system except Earth. Compare the three environments directly and the differences become starkly clear. Earth has one atmosphere of pressure at sea level, 78% nitrogen, 21% oxygen, breathable and protective. Mars has 0.006 atmospheres, mostly carbon dioxide, unbreathable, provides no meaningful radiation shielding, requires full pressure suits for any surface activity. Titan has 1.448 atmospheres, 95% nitrogen, 5% methane, unbreathable, but non-toxic, provides full radiation shielding, requires heated clothing and a breathing mask, but not a pressure suit. One of those environments is fundamentally hostile. One is fundamentally protective, and the protective one isn't Earth, it's Titan. The fact that no one talks about this outside of niche planetary science circles is baffling, until you remember that Titan is 886 million miles away, and most people stopped paying attention after the word million. Distance has dominated the conversation so completely that the actual properties of the destination get treated as afterthoughts. Mars gets attention because it's close. The Moon gets attention because we've already been there. Titan gets a footnote in documentaries about Saturn and a brief mention in discussions of astrobiology because it has organic chemistry. The atmosphere, the single most important feature for human habitability, gets glossed over or reduced to a bullet point in a list of interesting facts. But the atmosphere is the whole game. It's the reason Titan isn't just another frozen rock. It's the reason the Moon has weather, has liquid on the surface, has processes running that shape geology in real time. It's the reason Titan can shield its surface from radiation without requiring anyone to build the shield. It's the reason you could walk outside in relatively lightweight gear instead of a full EVA suit. It's the reason transport can happen by air instead of ground. It's the reason habitats don't have to be buried. And it's the reason Titan, despite being 15 times farther from the Sun than Mars, is a more practical destination for long-term human presence than anywhere else we've seriously considered. The atmosphere didn't happen by accident. Titan has managed to hold onto its air for billions of years because the Moon is massive enough, about 40% larger than Earth's moon and bigger than the planet Mercury, that its gravity can retain nitrogen and methane even at distances from the Sun where solar heating is minimal. Saturn's magnetosphere, the magnetic bubble generated by the gas giant's interior, also provides some protection from the solar wind that would otherwise strip lighter gases away over geological timescales. Titan sits inside that bubble, sheltered by its parent planet in a way that Mars never was after its own magnetic field died. The result is an atmosphere that has persisted, that continues to cycle through weather patterns, that rains methane onto the surface where it flows into rivers and pools in seas, and evaporates back into the air to start the cycle over. A stable, self-maintaining system that has been running since long before humans existed, and will keep running long after we're gone. We didn't build it. We didn't terraform it. We didn't engineer it. It's just there, waiting, doing the job that every atmosphere does when left alone. Shielding, moderating, cycling, protecting. The engineering advantages compound. Pressure suits are expensive, complex, and limited in operational lifespan. Each suit requires custom fitting, regular maintenance, and eventual replacement. Supplying a Mars colony with enough suits to keep a workforce mobile means a constant logistics tale of spare parts, replacement units, and repair facilities. On Titan, the equivalent gear is simpler. Insulated clothing isn't exotic. Heating elements are mature technology. Oxygen supplies are the same systems used in high-altitude mountaineering or emergency equipment on aircraft. Scaled for longer duration, but not fundamentally different. The supply chain gets simpler. The failure modes get less catastrophic. The cost per person drops. Radiation shielding on Mars means mass, lots of it. Regolith piled on roofs, thick walls, underground construction. Every kilogram of shielding is a kilogram that either had to be launched from Earth at enormous cost or excavated and moved on Mars using equipment that also had to be launched from Earth. It's a resource sink that never stops consuming labor and energy. On Titan, the shielding is free. The atmosphere is already there. You don't haul it. You don't maintain it. You don't replace it. You just build your habitat under it, and the protection comes standard. The gravity difference matters for health too. Mars has about 38% of Earth's gravity. Titan has 14%. Both are low enough that long-term health effects are uncertain. We know that zero gravity causes bone density loss, muscle atrophy, fluid shifts, vision problems. We don't know where the threshold is below which those effects become irreversible, or where they level off into a manageable equilibrium. But lower gravity makes everything easier in terms of mechanical work. Moving is easier, lifting is easier, construction is easier. And if the trade-off is health effects that might require exercise regimens or pharmaceutical interventions, that's a trade-off every environment off Earth is going to force. Titan doesn't make gravity go away, but it pairs low gravity with an atmosphere that makes the low gravity an asset instead of just a liability. The flight capability alone is worth lingering on because it changes what exploration looks like. On Mars, rovers are ground-bound. They move slowly, a few kilometers per day at best, navigating around obstacles limited by terrain. A Mars helicopter, the Ingenuity drone that flew alongside the Perseverance rover, managed short hops of a few hundred meters and was considered a breakthrough because Mars' thin atmosphere makes rotor flight barely possible. On Titan, flight is the default. You're not fighting for lift. You're throttling it back to avoid going too fast. Aerial survey becomes trivial. Cargo transport becomes routine. Personnel movement happens in minutes instead of hours or days. Picture a Titan base with a landing pad instead of a garage. Picture resupply missions that don't require ground vehicles threading through canyons or over ridges. Picture emergency response that can reach an accident site anywhere within a 100-kilometer radius in under an hour. That's the operational tempo Titan's atmosphere enables. You're not crawling across a hostile surface in a metal box. You're flying over it in a vehicle that could be as simple as a powered hang glider with an oxygen supply and a heater. The atmosphere also moderates temperature swings in a way that vacuum environments can't. The moon goes from 120 Celsius in sunlight to negative 130 in shadow. Mars swings from about 20 Celsius at the equator during the day to negative 73 at night. Those swings stress materials, complicate thermal management, and require active heating and cooling systems that run constantly. Titan's thick atmosphere acts as a thermal buffer. Surface temperatures stay around negative 179 Celsius, cold but stable. Day-night temperature variation is minimal, a few degrees at most. Seasonal variation exists, driven by Saturn's 29.5-year orbit around the Sun, but even that is muted compared to what you'd see on an airless body. Stable temperatures mean simpler engineering. Your habitat doesn't need to survive a 250-degree temperature range. Your materials don't expand and contract wildly every 12 hours. Your thermal regulation system doesn't have to fight against wild swings in external conditions. You're designing for cold, yes, extreme cold, but cold that doesn't change much. That's a narrower design envelope. Narrower envelopes mean cheaper, lighter, more reliable systems. And beneath all of this, underneath the radiation shielding and the pressure and the flight capability, is the simple fact that Titan's atmosphere makes the place feel less alien. You can't see that in data. You can't quantify it in a spreadsheet. But human psychology responds to environments. Standing on the Moon or Mars, you're looking at a sky that's black or near black even during the day. You're seeing stars in daylight because there's no atmosphere to scatter light. You're surrounded by silence because there's no air to carry sound. It's beautiful in a stark, lifeless way, but it's not a place that feels habitable. It feels like space, like you're standing on a rock in a void. On Titan, you'd see a sky, not black, orange, hazy, thick with aerosols and organic particles scattering light. You'd see clouds, you'd see weather developing, storms moving across the horizon, maybe methane rain falling in the distance. You'd hear wind, muffled through your suit but present, moving through the atmosphere, interacting with the surface. It wouldn't sound like Earth. The acoustics would be different, the frequencies shifted by the density and composition of the air, but it would sound like something. Like a world that has processes running, where the environment is active and dynamic instead of frozen in geological time. That difference might be the most important one. Mars and the Moon feel dead because they are dead. Titan feels alive because it is alive. Not biologically, we don't know that yet, but geologically and atmospherically. It has weather, it has seasons, it has liquids moving across the surface, carving channels, filling lakes, evaporating and raining back down. It has chemistry happening in real time, methane and nitrogen, and more complex hydrocarbons interacting, reacting, building molecules that might be precursors to something we'd recognize as prebiotic. The atmosphere is the engine driving all of that. Without it, Titan would be another frozen ice ball. With it, Titan is a world in motion. We've spent so long assuming that habitability meant Earth-like that we missed the broader definition. Habitability doesn't require oxygen. It doesn't require liquid water on the surface. It doesn't require temperatures in the range humans evolved to tolerate. Habitability requires protection from radiation, stable pressure, and an environment that doesn't actively kill you faster than you can adapt. Titan delivers all three. The atmosphere is the shield, the buffer, the baseline that makes everything else possible. It's the reason Titan isn't just scientifically interesting, but practically viable. The reason a colony there wouldn't be a bunker clinging to survival, but a settlement building infrastructure in an environment that, while cold and strange, isn't fundamentally trying to erase you. Mars had an atmosphere and lost it. The Moon never had one. Earth has one and we take it for granted. Titan has one, thicker than ours, and it's been sitting there in the outer solar system for billions of years doing exactly what atmospheres do: shielding, moderating, cycling, protecting, waiting for someone to notice that 886 million miles isn't too far if what's waiting at the other end is the only place beyond Earth where the air itself does half the work of keeping you alive. We've established that Titan has an atmosphere, a real one, thicker than Earth's, protective enough to make pressure suits unnecessary and dense enough to make flying trivial. That alone places Titan in a category of 1 when it comes to habitable destinations beyond Earth. But the atmosphere is only half the story. The other half is sitting on the surface, pooled in basins, flowing through channels, falling from clouds as rain. Liquid, not water. Methane and ethane, hydrocarbons that stay liquid at negative 179 degrees Celsius, cycling through an active weather system that mirrors Earth's hydrological cycle in almost every detail except the chemistry. And the sheer volume of that liquid, the reserves sitting in Titan's lakes and seas and soaked into the subsurface, represents an energy stockpile so vast that it makes Earth's entire fossil fuel economy look like a regional mining operation. The first confirmed detection of liquid on Titan's surface came in January 2007, announced by the Cassini mission team after analysing radar data collected the previous July. Radar works by bouncing radio waves off a surface and measuring how much signal comes back. Smooth surfaces reflect cleanly, rough surfaces scatter the signal. Liquids, because they're flat and uniform at large scales, reflect almost nothing back to the source. They show up on radar as dark patches, voids where the signal vanished into the surface instead of bouncing back. Cassini's radar saw those voids near Titan's North Pole. Dark, smooth, completely non-reflective regions shaped like shorelines, inlets, bays, lakes, hundreds of them. That shouldn't have been possible. Liquid methane and ethane on a surface exposed to space, even with an atmosphere, should evaporate. The vapor pressure of methane at Titan's surface temperature is high enough that any small body of liquid should sublimate into the air within decades or centuries, geological eye blinks. For lakes to persist, they have to be fed, replenished, which means Titan isn't just passively holding on to ancient reserves, it's cycling them. Methane evaporates from the surface into the atmosphere, rises, cools, condenses into clouds, and falls back to the ground as rain. That rain flows downhill into rivers, streams, and eventually lakes and seas. The lakes feed back into the atmosphere through evaporation, and the cycle continues. A weather system, active, ongoing, stable enough to maintain liquid bodies on the surface for at least as long as we've been observing them, and likely far longer. The named lakes started piling up as Cassini continued mapping. 32 named lakes by the time the mission ended, most of them clustered near the North Pole where conditions favour liquid methane stability. The South Pole has fewer, possibly because of seasonal variations in solar heating driven by Saturn's 29.5-year orbit around the Sun. Titan's seasons are long. Summer at one pole lasts about 7.5 Earth years, then shifts to the other pole. The North Pole was coming out of winter when Cassini arrived, which may explain why so many lakes appeared there fully stocked, while the South looked drier. By the time Cassini's mission ended in 2017, seasonal changes were starting to shift the balance, with some northern lakes showing signs of shrinkage and southern regions showing possible new liquid accumulation. Then there are the seas, not lakes, seas. 3 of them large enough to earn the designation, each one covering an area comparable to major bodies of water on Earth. Kraken Mare, the largest, spans roughly 400,000 square kilometres, bigger than the Caspian Sea. Ligeia Mare, the second largest, covers about 126,000 square kilometres, roughly the size of Lake Michigan and Lake Huron combined. Punga Mare, the smallest of the 3, still dwarfs most lakes on Earth. These aren't puddles. They're not temporary features left over from a wetter epoch in Titan's history. They're active, filled, maintained by rainfall and subsurface seepage, deep enough that Cassini's radar measured depths exceeding 100 metres in some lakes and close to 200 metres in Ligeia Mare. Deep enough to drown in, deep enough to require boats if you wanted to cross them, deep enough that the bottoms are invisible from the surface, hidden beneath liquid methane that's clearer than water, but still opaque over distance. The composition came from spectroscopy, analysing how light reflects off the liquid surfaces and how radar signals interact with the material. The lakes and seas are mostly methane with significant ethane mixed in, along with trace amounts of propane, acetylene and other light hydrocarbons. Methane dominates because it's the most volatile, the easiest to evaporate and the first to condense out of the atmosphere when temperatures drop. Ethane is a byproduct of methane photolysis, the process where ultraviolet light from the sun breaks methane molecules apart high in the atmosphere. The freed hydrogen escapes into space, the remaining carbon and hydrogen recombine into more complex molecules, and ethane is one of the most common results. Over geological time, ethane accumulates in the lakes and seas, mixing with methane, creating a hydrocarbon soup that shifts in composition depending on local conditions and seasonal cycles. NASA's estimates of the total hydrocarbon reserves on Titan are staggering, and they've been stated multiple ways depending on which aspect of the system you're measuring. The visible lakes and seas contain liquid hydrocarbons equivalent to roughly 300 times Earth's proven oil reserves. That's not an estimate. That's a direct measurement based on radar mapping of surface area and depth, combined with spectroscopic analysis of composition. 300 times all the oil we've confirmed exists in accessible reservoirs on Earth. Saudi Arabia, Russia, the United States, Venezuela, every oil field, every offshore platform, every reserve counted in the global energy supply, multiply it by 300, and you're still only accounting for what's sitting on Titan's surface in liquid form. Another way to frame it, Titan's lakes and seas represent about 35 times the mass of Earth's total fossil fuel reserves, oil and natural gas combined. That includes coal, which is mostly carbon, and natural gas, which is mostly methane, the same compound Titan has in bulk. The mass comparison accounts for the fact that Titan's hydrocarbons are lighter per unit volume than Earth's crude oil, which is a thick mix of longer chain molecules. Methane and ethane are simpler, lighter, but the sheer volume compensates for the lower density. 35 times everything we've ever burned or could burn if we kept digging, and that's just the liquid on the surface. The atmosphere contains more. Cassini's atmospheric measurements showed that Titan's air holds about 7 times more methane than the exposed liquid reservoirs. That methane is cycling, condensing into rain, falling to the surface, evaporating back up. Some of it stays in the atmosphere, some of it ends up in the lakes, some of it soaks into the subsurface, Titan's version of groundwater, except it's ground methane, saturating the upper layers of ice and rock, waiting to seep out wherever the terrain dips low enough to expose it. If you add up the atmospheric reserves, the surface lakes and seas, and the subsurface methane-saturated layers that must exist to maintain the whole system, the total hydrocarbon budget on Titan exceeds anything Earth has ever had access to by orders of magnitude. And unlike Earth's fossil fuels, which took hundreds of millions of years to form from the buried remains of ancient life, Titan's hydrocarbons are primordial. They've been there since the Moon formed, part of the original material that coalesced from the solar nebula 4.5 billion years ago. They didn't require biology. They didn't require time. They're just sitting there, part of the inventory, renewable on timescales of millions of years as methane gets replenished from deeper reserves or possibly from chemical reactions in Titan's interior. That replenishment has to be happening. Methane in Titan's atmosphere is photolyzed by sunlight, broken apart into hydrogen and more complex hydrocarbons. The hydrogen escapes. The complex molecules rain down and accumulate on the surface or in the lakes. Left unchecked, That process would strip all the methane out of Titan's atmosphere in about 10 to 100 million years, a short span in geological terms. The fact that Titan still has methane, and lots of it, means something is replacing what's lost. Either there's a massive subsurface reservoir feeding methane up through cracks and vents, or chemical reactions deep inside Titan are generating new methane from water and rock, a process called serpentinization that happens on Earth in certain geological settings and has been proposed for icy moons like Enceladus. Either way, Titan's methane supply isn't running dry anytime soon. The system is active, maintained, cycling on timescales that make human exploitation irrelevant to the moon's overall budget. For a colony, that's the entire energy problem solved before you even land. Every rocket needs fuel, every habitat needs heat, every piece of machinery needs power. On Mars, you're generating power from solar panels that produce a fraction of what they'd produce on Earth, because sunlight at Mars's distance is already 40% weaker, and dust storms cut it further. Or you're running nuclear reactors, which require shipping fissile material from Earth, and maintaining complex machinery in a dust-filled environment. On the Moon, solar works better because there's no atmosphere to scatter light, but you're dealing with 2-week nights and temperature swings that stress every system. On Titan, you land next to a lake, drop a hose and start pumping methane. Methane is fuel, not exotic fuel, not experimental fuel. The same methane that heats homes and powers electrical plants on Earth, the same natural gas that flows through pipelines across continents. It burns cleanly in the presence of oxygen, producing carbon dioxide and water vapor. 1 molecule of methane plus 2 molecules of oxygen yields 1 molecule of carbon dioxide, 2 molecules of water, and a significant release of energy. The chemistry is straightforward. The only requirement is oxygen, which you're already producing for life support by splitting water into hydrogen, and oxygen using electrolysis. Use some of that oxygen to burn methane and you have heat, electricity, propulsion, whatever you need. The energy density of methane is high, about 55 megajoules per kilogram, comparable to gasoline. A kilogram of methane burned with the right amount of oxygen releases enough energy to lift roughly 200 kilograms to low Earth orbit, accounting for inefficiencies in rocket engines. On Titan, with lower gravity, the same energy gets you much farther. Lifting off from Titan's surface requires about half the delta V of lifting off from Earth. A methane-oxygen rocket, fueled entirely from local resources, could launch cargo into Titan orbit, rendezvous with interplanetary spacecraft, and return to the surface for refueling. No need to ship fuel from Earth. No need to ration propellant. The resource is sitting there in the lakes, effectively unlimited, waiting to be used. Beyond propulsion, methane solves the heating problem, and on Titan, heating is not optional. Surface temperatures sit at negative 179 Celsius. Habitats need constant heat to stay above freezing. Water-based life support systems freeze solid if the temperature drops below 0 Celsius. Electronics have minimum operating temperatures. Humans need environments in the range of 15 to 25 Celsius to stay comfortable and healthy long-term. Maintaining that temperature differential, warming the inside of a habitat to room temperature, while the outside sits at nearly 200 degrees below zero, requires continuous energy input. Burning methane provides that input directly. Heat exchangers, standard technology on Earth, transfer thermal energy from combustion exhaust into the habitat's air or water-based heating system. The only consumable is oxygen, and you're producing that anyway from water electrolysis. The methane is free, the heat is on demand, the system scales linearly with colony size. More habitats, more heating, more methane burned, but the lake you're drawing from contains more fuel than you could burn in 1,000 years of continuous operation, even if you scaled up to a city. Then there's chemical feedstock, the industrial side of hydrocarbons that gets less attention than fuel, but matters just as much for long-term sustainability. Methane and ethane are not just burnable, they're buildable. Carbon and hydrogen, the 2 elements that make up hydrocarbons, are the basis for a staggering range of materials. Plastics, polymers, synthetic fibers, lubricants, solvents, pharmaceuticals, fertilizers. Most of modern industry starts with hydrocarbons, breaking them apart and reassembling the pieces into more complex molecules tailored for specific purposes. On Earth, we extract crude oil from the ground, refine it into fractions based on molecular weight, and feed those fractions into chemical plants that produce everything from polyethylene bottles to nylon clothing to synthetic rubber. The process requires energy, catalysts and infrastructure, but the chemistry itself is mature. We've been doing it for over a century. Titan offers the raw material in bulk, simpler and purer than crude oil because it's not a mix of hundreds of different compounds. It's methane and ethane, clean, easy to separate, ready to feed into whatever reaction you need. Want plastics? Polymerize ethylene, which you get from methane by removing hydrogen in a catalytic cracker. Want insulation? Produce polystyrene or polyurethane foams, both hydrocarbon-based. Want structural composites? Build carbon fiber from methane by pyrolyzing it at high temperatures to break it down into elemental carbon and hydrogen. The hydrogen becomes fuel or gets vented. The carbon becomes fibers stronger than steel by weight. Every material you'd need to expand a colony, to build new habitats, to manufacture tools and equipment and replacement parts, can be synthesized from the hydrocarbons sitting in Titan's lakes. That's the circular economy NASA keeps referencing when they talk about Titan as a potential destination. A circular economy doesn't rely on continuous resupply from Earth. It relies on local resources cycling through the system, used, transformed, reused. On Titan, you pump methane from a lake, burn some of it for heat and power, crack some of it into simpler molecules for chemical synthesis, polymerize those molecules into plastics and materials, and when those materials wear out or break, you can pyrolyze them back into hydrocarbons and start over. The only inputs are energy, which you're generating from burning methane or from nuclear sources, and occasional replenishment of trace elements and catalysts that can't be sourced locally. The bulk of the industrial base runs on what's already there. Compare that to Mars. Mars has carbon dioxide in the atmosphere, about 95%, which can be split into carbon monoxide and oxygen using energy. The oxygen is useful for life support and propellant. The carbon monoxide can be reacted with hydrogen to produce methane and water through the Sabatier process, another mature technology. But the hydrogen has to come from somewhere, which means either mining water ice from the Martian poles or subsurface deposits and splitting it into hydrogen and oxygen, or shipping hydrogen from Earth. And the energy required to run the Sabatier reactor, to split CO2, to electrolyze water, all of that has to come from solar panels or nuclear reactors operating in a dust-choked environment. You can make fuel on Mars, you can make materials, but every step requires energy and infrastructure fighting against an environment that offers no free resources beyond carbon dioxide and frozen water. On Titan, the fuel is liquid. You pump it. You don't mine it. You don't extract it from the air with complex machinery. You don't crack it out of frozen regolith. You walk up to a lake with a hose and fill a tank. The energy cost is a pump and a heater to keep the lines from freezing. The infrastructure is a storage tank and a distribution network. It's the difference between running a chemical plant and running a gas station. Then there's the scale of the reserves, which keeps coming back because the numbers are absurd and they don't stop being absurd no matter how many times you state them. Titan's visible surface liquids, 300 times Earth-proven oil reserves, are enough to fuel human civilization at current consumption rates for tens of thousands of years. That's assuming you're burning it at Earth's industrial scale, which you wouldn't be. A Titan colony, even a large one, wouldn't consume hydrocarbons at a rate anywhere near Earth's total usage. Earth burns about 100 million barrels of oil per day, roughly 15 billion litres. That's powering 8 billion people, billions of vehicles, thousands of power plants, the entire global industrial base. A Titan colony of 10,000 people, even with heavy industrial activity, would burn a tiny fraction of that. The lakes wouldn't noticeably drain. The seas wouldn't drop. You could run a colony the size of a city for centuries without making a dent. And the replenishment mechanism, whatever it is, means the reserves aren't static. Methane is being added to the system over time, seeping up from the interior, replacing what's lost to photolysis and consumption. The timescale for replenishment is 10 to 100 million years, long by human standards, irrelevant by geological ones. A human presence on Titan would be operating on such a short timescale compared to the Moon's natural cycles that the colony's fuel use would register as noise in the overall system. You're not mining a finite reserve, you're tapping a renewable flow that happens to be measured in millions of tons per year instead of litres per day. The hydrocarbon cycle itself, the methane weather system, is worth understanding because it drives the distribution and accessibility of the resource. Methane evaporates from lakes and seas at a rate determined by surface temperature, which varies slightly with latitude and season. The vapor rises into the atmosphere, mixing with nitrogen, carried by winds that can reach several meters per second at altitude. When the vapor-rich air cools, either by rising to higher altitudes or by moving toward the poles during colder seasons, the methane condenses into droplets. Clouds form. Those clouds eventually precipitate, raining methane back to the surface. The rain flows downhill, carving channels, eroding terrain, pooling in basins. Some of it soaks into the subsurface, some of it refills lakes and seas, and the cycle repeats. The rainfall is sporadic, not constant. Cassini observed evidence of methane storms, intense precipitation events that darkened large areas of Titan's surface as fresh liquids spread over dry terrain. Those events are seasonal, tied to changes in solar heating, as Saturn's orbit carries Titan closer to or farther from the Sun over the course of its 29-year cycle. During Titan's northern summer, the North Pole receives more sunlight, heating the lakes, increasing evaporation rates, feeding cloud formation that eventually dumps rain back down. The South Pole, in shadow during northern summer, sees less precipitation. The system oscillates, shifting the balance of liquid from one hemisphere to the other over decades. That oscillation matters for planning. A colony near the North Pole would have easy access to liquid methane most of the time. But during southern summer, some of those lakes might shrink as evaporation exceeds rainfall. A colony positioned near a major sea like Kraken Mare or Ligeia Mare wouldn't have that problem. The seas are large enough that seasonal evaporation barely affects their total volume. They're stable reservoirs, deep enough and extensive enough that they act as buffers, absorbing seasonal fluctuations without drying up. One odd detail from a 2006 study looked at how fast shorelines on Titan could migrate under different conditions. The researchers modelled lake dynamics, factoring in evaporation, precipitation, and subsurface seepage, and found that shorelines could shift by hundreds of meters to tens of kilometers per year, depending on the lake's size and the local weather. That sounds dramatic until you remember the timescales. A 10-kilometer shoreline shift over a year is still slow enough to plan around. You don't build your dock on unstable terrain. You build it where the bathymetry suggests deep water close to shore, where seasonal changes won't strand your infrastructure. But the fact that the shorelines move at all, that Titan's lakes are dynamic enough to reshape their boundaries over human observable timescales, reinforces how active the system is. These aren't frozen relics. They're living features, responding to weather, to seasons, to the same kinds of hydrological processes that shape coastlines and rivers on Earth. The organic content extends beyond the lakes. Titan's surface is covered in dunes near the equator, vast fields of dark material shaped by wind into linear ridges hundreds of kilometers long. Cassini's instruments analyzed the composition and found hydrocarbons, complex organic molecules heavier than methane, possibly tholins, a catch-all term for the reddish-brown gunk that forms when methane and nitrogen are exposed to ultraviolet light or cosmic rays. That material, the stuff in the dunes, has been compared in mass and organic content to Earth's total coal reserves. Not methane, not liquid fuel, but solid hydrocarbons, rich in carbon, potentially usable as feedstock for chemical synthesis if you needed something denser than methane, or if you wanted to extract elemental carbon without running a high-temperature reactor. The resource base on Titan isn't just deep, it's diverse. Liquid methane and ethane for fuel and chemical feedstock. Atmospheric methane for supplemental supply. Solid organics in the dunes for carbon extraction. Water ice in the crust for oxygen and hydrogen production. Nitrogen in the atmosphere for fertilizers, and industrial processes that require inert gas. Trace hydrocarbons, propane, acetylene, benzene, scattered through the system in concentrations low enough that they didn't dominate Cassini's measurements, but high enough that targeted extraction could supply niche industrial needs. You're not landing on a resource-poor rock where every atom has to be justified and rationed. You're landing on a moon that has more of the basic building blocks of industry than you could use in 1,000 years of expansion. The economic argument writes itself. A colony on Titan would be energy independent from day one. Fuel costs drop to the price of pumping and transport. Material production scales with local demand sourced from lakes and atmosphere without needing Earth-based resupply. The only imports would be things Titan doesn't have, metals for electronics, rare earth elements for certain technologies, maybe biological starter cultures if you're setting up agriculture. Everything else, the bulk materials, the energy, the chemical feedstocks, comes from the moon itself. That's not just sustainability, That's self-sufficiency on a scale that no other destination in the solar system can offer. Mars makes you fight for every resource. The Moon makes you dig and process and scrape by. Earth orbit makes you dependent on a supply chain stretching back to the surface. Titan hands you a lake of fuel and says help yourself. The difference is existential. A Mars colony would always be fragile, one broken supply line away from catastrophe, always dependent on Earth for the resources it can't extract locally. A Titan colony would be robust, able to expand, able to build, able to sustain itself even if contact with Earth were severed for years or decades. The resource base makes independence possible, and independence is what separates an outpost from a civilization. The circular economy loops back to another point. Titan's hydrocarbons aren't just fuel and materials, they're also the basis for chemistry that could support life, or at least the precursors to life. Organic molecules, carbon-based compounds, the building blocks that on Earth eventually assembled into amino acids, nucleotides, lipids, all the pieces that make biology work. Titan's lakes and atmosphere and surface are soaking in organics, complex molecules that have been reacting with each other for billions of years under conditions that favour chemical experimentation. No one knows if those reactions have produced anything that qualifies as life. No one knows if Titan's chemistry has crossed the line from complex organic molecules to self-replicating systems. But the fact that the chemistry is happening, that the environment supports it, that the raw materials are abundant and constantly cycling through different states and conditions, means Titan is the best laboratory in the solar system for studying how life might begin in environments that don't look like Earth. And if we find that Titan's chemistry has independently arrived at something biological, something that metabolizes, reproduces, evolves, then the Moon stops being just a resource depot. It becomes the second example of life in the universe, the proof that biology isn't a fluke tied to water and warm temperatures, but a process that can happen wherever chemistry gets complicated enough and conditions stay stable long enough. That discovery, if it happens, would come from the same lakes we're talking about mining for fuel. The same organic-rich environment that makes Titan a practical destination for colonization is the environment that makes it a probable site for life. And navigating that tension between exploiting the resource and preserving the discovery would be the defining challenge of any Titan mission. But that's a question for later. First, we have to understand what's in those lakes, what reactions are running, what chemistry is possible when methane takes the place of water and organic molecules pile up faster than they break down. We've established that Titan is sitting on an energy stockpile that makes Earth's fossil fuel reserves look like a gas station's weekly inventory. Lakes of methane, seas of ethane, an atmosphere thick with hydrocarbons cycling through weather patterns that mirror Earth's water cycle down to the details. That's the resource side, the practical answer to how a colony survives and thrives 886 million miles from the Sun. But there's another question buried underneath all that chemistry, one that matters more than fuel efficiency or materials production. It's the question that drives half of planetary science and keeps astrobiologists employed. Does Titan have life? Not life as we know it. That phrase gets overused to the point of meaninglessness, but in Titan's case it's the only accurate description. If there's biology on Titan, and that's a very large if, it won't be anything that resembles the carbon-water-based chemistry that runs every organism on Earth. It would be something else. Something adapted to temperatures so cold that water turns into rock and methane stays liquid. Something that uses different solvents, different energy sources, different molecular machinery. Life, but built on a blueprint so alien that we might not recognize it, even if we were looking directly at it. The idea has a name: cryo-life, life in the cold, life that operates at temperatures where Earth biology would freeze solid in seconds, where chemical reactions slow to a crawl, where the usual rules about metabolism and replication stop applying. It sounds like science fiction until you remember that Titan has all the ingredients. Liquid solvent, check. Methane and ethane lakes covering hundreds of thousands of square kilometers. Energy sources, check. Sunlight, weak but present. Chemical energy from the breakdown of complex organics. Possibly geothermal energy seeping up from the interior. Organic molecules, check in abundance. The atmosphere is a chemical factory producing complex hydrocarbons, tholins, nitriles, molecules with 5, 10, 20 atoms linked together in chains and rings. Chemistry happening constantly, driven by ultraviolet light from the sun, and cosmic rays slamming into the upper atmosphere, breaking bonds, forming new ones, building complexity out of simple starting materials. The question isn't whether Titan has the pieces. It demonstrably does. The question is whether those pieces have assembled into something that qualifies as alive, something that takes in energy, maintains itself against entropy, reproduces, evolves, something that crosses the line from chemistry to biology. Nobody knows. We don't have the data yet. But the possibility is real enough that NASA, ESA, and every major space agency with an astrobiology program takes it seriously. Titan is one of the highest priority targets in the solar system for the search for life, not because we've found evidence of life there, but because the environment makes it plausible in a way that most places don't. Mars might have had life billions of years ago when it still had liquid water and a thicker atmosphere. Europa and Enceladus might have life now in their subsurface oceans. But Titan is the only place besides Earth where the surface itself, the part we can see and sample and study, host active chemistry in liquid environments that have been stable for billions of years. If life can start in hydrocarbon lakes under a nitrogen sky at negative 179 degrees Celsius, Titan is where it would happen. The chemistry is worth walking through because it's not intuitive. On Earth, life uses water as a solvent. Water is the medium in which biochemistry happens. Proteins fold in water, DNA replicates in water. Cells are mostly water, membranes holding aqueous solutions of enzymes and nutrients and waste products. Water works because it's a polar molecule, one end slightly positive, the other slightly negative, which makes it excellent at dissolving other polar molecules and ions. Salts, sugars, amino acids, all the building blocks of terrestrial life, dissolve readily in water and stay dissolved long enough for chemical reactions to occur. Methane and ethane are non-polar. They don't dissolve the same things water does. Salts don't dissolve in methane. Sugars don't. Most of the molecules that make up Earth life would be insoluble in a methane lake, unable to move, unable to react. But other molecules, the ones that are non-polar or only weakly polar, dissolve just fine. Long-chain hydrocarbons, oils, fats, complex organic molecules with mostly carbon and hydrogen backbones, those are soluble in methane. And Titan's lakes and atmosphere are full of exactly those molecules. So if there's life in Titan's lakes, it's not using the same biochemistry we use. It's using something else. Maybe membranes made of compounds that stay flexible at cryogenic temperatures, something like polyethylene or other long-chain hydrocarbons that can self-assemble into barriers separating inside from outside. Maybe metabolic pathways that extract energy from reactions between methane and other hydrocarbons, or between organics and trace oxidizers like oxygen or nitrogen compounds mixed into the lakes. Maybe genetic material that's not DNA or RNA but some other polymer capable of storing information and replicating in liquid methane. This isn't idle speculation. Astrobiologists have been modelling hypothetical methane-based life for decades, publishing papers with titles like Life in Liquid Methane and Azotosms, Stable Membrane-Forming Vesicles in Liquid Methane. That second one, published in 2015, proposed that nitrogen-based compounds could form cell-like structures in liquid methane, stable vesicles with membranes flexible enough to function as barriers at Titan-like temperatures. The researchers called them azotosms, from azote, an old name for nitrogen. They're not cells in the traditional sense, they're just structures that could in principle do what cell membranes do. Separate an interior from an exterior, allow selective transport of molecules, maintain chemical gradients. The basic requirements for something that could house biochemistry. Whether azotosomes or anything like them actually exist on Titan is unknown. The study was theoretical, computer modelling of molecular interactions at low temperatures. But the fact that the structures are theoretically stable, that the chemistry allows them, means cryolife isn't ruled out by physics. It's allowed. Whether it's likely is a different question, one we won't answer until we can sample Titan's lakes directly and analyse what's in them at the molecular level. There's another possibility, one that doesn't require inventing new biochemistry. Titan has a subsurface ocean. Not on the surface, buried deep under the ice shell, a layer of liquid water trapped between the frozen crust and the rocky core. Cassini confirmed this indirectly through gravity measurements during close flybys of Titan. The way Titan's shape deformed slightly in response to Saturn's tidal forces bulging and flexing as it orbited indicated that something liquid was sloshing around inside. Solid ice wouldn't deform the same way. A liquid layer would, and the best fit to the data was an ocean of water mixed with ammonia or salts to lower the freezing point, sitting anywhere from 50 to 100 kilometers below the surface. That ocean is probably in contact with Titan's rocky core, which means it could be fed by hydrothermal vents, hot water seeping up from the interior where tidal heating and radioactive decay keep things warm. If that's the case, Titan's subsurface ocean might be chemically similar to Earth's deep-sea hydrothermal systems, the black smokers and white smokers that sit on mid-ocean ridges, spewing mineral-rich water into the cold abyssal depths. On Earth, those vents support thriving ecosystems. Tube worms, clams, crabs, bacteria that metabolize hydrogen sulfide and methane seeping from the vents, entire food webs disconnected from sunlight, running on chemical energy instead of photosynthesis. If Titan's subsurface ocean has vents, and if those vents have been active for billions of years, then Titan might host life as we know it, water-based, carbon-based, biochemistry that would be recognizable to a terrestrial biologist even if the specific organisms were alien. That's the 2-for-1 scenario astrobiologists get excited about. Titan as a testing ground for 2 independent origins of life, one in the methane lakes on the surface using exotic chemistry, one in the water ocean below using familiar chemistry. 2 separate experiments running on the same moon, both potentially habitable, neither one guaranteeing life but both offering conditions that make it possible. The discovery of Mimas's ocean complicated the picture and made it more interesting. Mimas, another of Saturn's moons, smaller than Titan, closer to Saturn, heavily cratered and unremarkable in appearance, turned out to have a subsurface ocean too. Cassini data combined with later analysis revealed that Mimas's interior was sloshing in a way that required liquid water. That was a surprise because Mimas is small, only about 400 kilometers across, and it's heavily cratered, which suggested its surface had been frozen solid for billions of years, with no recent geological activity. Yet it has an ocean, hidden beneath an ice shell that shows no obvious cracks or fractures or signs of communication between the surface and the interior. If Mimas, a dead-looking moon with no atmosphere and no surface activity, can maintain a liquid ocean for potentially billions of years, then the criteria for habitable subsurface oceans just got a lot looser. It's not just the big moons like Europa and Titan. It's potentially dozens of mid-sized icy moons throughout the outer solar system, each one possibly harbouring a hidden ocean that never interacts with the surface. Isolated, stable, warm enough to stay liquid, possibly warm enough to support chemistry. Titan's ocean stops being unique and starts being an example of a broader category. And if subsurface oceans are common, then the number of potentially habitable environments in the solar system jumps from a handful to dozens or more. Titan's advantage over most of those other ocean worlds is that its surface and its interior might not be completely isolated. Cryovolcanism, the eruption of water or ammonia or methane from the interior onto the surface, has been proposed based on observations of certain features that look like they might be volcanic in origin. Not confirmed, but plausible. If cryovolcanoes exist on Titan, they would provide a direct pathway between the subsurface ocean and the surface environment. Material from the ocean, possibly including organic molecules or even microbes if the ocean is inhabited, could be erupted onto the surface where it would freeze, mix with surface organics, and potentially get washed into the methane lakes by rainfall. That mixing, if it happens, would create an environment where water-based chemistry and methane-based chemistry overlap, where molecules from 2 completely different chemical regimes react, form new compounds that wouldn't exist in either system alone. That's the kind of environment that astrobiologists dream about because it maximizes the chances for chemical complexity, for unexpected reactions, for the kind of serendipity that might push a system from prebiotic chemistry into something self-sustaining. Prebiotic chemistry is the step before life, the stage where organic molecules get complicated enough and organized enough that they start doing things that resemble biology without quite crossing the line. On Earth, prebiotic chemistry probably happened in tidal pools, hydrothermal vents, maybe in clay-lined ponds where minerals catalyzed reactions between simple organics. Over time, hundreds of millions of years, chemistry stumbled its way into self-replicating molecules, primitive membranes, metabolic cycles. The exact path is still debated. Nobody was there to watch, but the end result was life, biology that took over the planet and hasn't stopped since. Titan is running a similar experiment, just with different starting materials. The atmosphere produces complex organics, tholins and nitriles and who knows what else. which rain down onto the surface and wash into the lakes. The lakes concentrate those organics, mix them together, expose them to trace amounts of water from the subsurface or from ammonia water ice melting at the bottom. Seasonal cycles drive temperature changes, evaporation and precipitation, which concentrate and dilute solutions, cycle materials through different chemical states. Energy flows in from sunlight, from cosmic rays, possibly from geothermal heat if cryovolcanism is active. All the ingredients for prebiotic chemistry are present. The process is running. The question is how far it's gotten. One of the strongest arguments for exploring Titan is that it's a natural laboratory for studying how life might begin in an environment that's nothing like the early Earth. Every sample we've collected, every experiment we've run, every model we've built about the origin of life on Earth is based on water, moderate temperatures, oxygen or lack thereof, carbon dioxide, nitrogen, phosphorus, the specific chemical environment that Earth offered 4 billion years ago. That's one data point, one example, and from one example, it's hard to know what's universal and what's contingent. Is water required for life, or is it just what Earth had available? Are the temperatures life originated at on Earth some kind of optimal range, or just what happened to exist in the right place at the right time? Is the specific chemistry we call biology inevitable given enough time and the right conditions, or is it a fluke, a low probability outcome that happened once and might never happen again? Titan offers a second data point, a completely different chemical environment, stable for billions of years, running its own version of prebiotic chemistry under conditions that have no overlap with early Earth. If we go to Titan, sample the lakes, analyze the surface organics, drill through the ice to sample the subsurface ocean, and we find life, or even just chemistry that's clearly on the way to becoming life, then we learn something fundamental about how common biology is in the universe. We learn that life isn't a fluke tied to Earth's specific history. It's a process that happens wherever chemistry gets complex enough and stable enough. The rules change, the solvents change, the temperatures change, but the outcome is the same: organization, complexity, self-replication, life. If we go to Titan and find nothing, no life, no biology, just chemistry that's interesting but not alive, we learn something different. We learn that life might be rare, that the jump from chemistry to biology might require specific conditions that Titan doesn't meet, that water might actually be necessary, or that temperatures need to be higher to drive reactions fast enough, or that time alone isn't enough without the right sequence of events. Either answer is valuable, either answer narrows the search space, tells us where else to look, helps us understand what makes a world habitable versus what makes it merely interesting. The scientific imperative to explore Titan is as strong as any target in the solar system. Mars gets attention because it's close, and because it might have had life in the past. Europa and Enceladus get attention because their subsurface oceans are in contact with rocky cores and might have hydrothermal vents feeding energy into the system. But Titan is the only place where we can study an active prebiotic chemistry lab on the surface, accessible, observable, running in real time. The only place where the conditions for life as we don't know it might actually exist. The only place where we might find two independent biospheres, one on the surface in methane, one below in water, both potentially inhabited, both offering answers to questions we've been asking since we figured out we were asking questions. NASA's Dragonfly mission, scheduled to launch in 2027 and arrive at Titan in the mid-2030s, is designed around these questions. It's a nuclear-powered rotorcraft, a quadcopter the size of a car, built to fly from site to site across Titan's surface sampling organics, measuring isotopic ratios, analysing atmospheric chemistry, looking for biosignatures, not life directly, biosignatures, chemical fingerprints that indicate biological processes are happening or have happened, unusual isotopic ratios that suggest metabolism, organic molecules in combinations that don't form easily through random chemistry, patterns in the distribution of compounds that suggest something is actively sorting them, concentrating them, using them. Dragonfly will land at Shangri-La, a field of dunes near Titan's equator, a region rich in organic material where seasonal methane rainfall occasionally darkens the surface as liquid soaks into the sand. From there, it'll fly to other sites, including Selk Crater, an impact site where liquid water from melted ice might have mixed with surface organics in the recent geological past. That mixing, water plus organics plus energy from the impact, is the kind of event that could jumpstart prebiotic chemistry, creating a concentrated burst of complex molecules in a small area. if there are biosignatures anywhere on Titan, an impact crater that briefly melted ice and mixed it with the organic-rich surface is a good place to look. Dragonfly won't find little green methane-breathing aliens swimming in Ligeia Mare. That's not what astrobiology looks like. It looks like mass spectrometry, chromatography, isotopic analysis. It looks like comparing the ratios of carbon-12 to carbon-13 in different organic samples and noticing that the ratios are skewed in ways that suggest biological fractionation. It looks like finding amino acids or nucleobases or lipids in combinations that are statistically unlikely to occur through random synthesis. It looks like patterns in data that tell you something non-random is happening, something organized, something that might be alive or might be on the way to becoming alive. And if Dragonfly finds nothing, if the chemistry on Titan turns out to be complex but lifeless, that's still an answer. It tells us life isn't inevitable. It tells us the universe is full of places that look habitable but aren't inhabited. It narrows the parameters, sharpens the search, focuses future missions on the targets most likely to yield results. But if Dragonfly finds something, even a hint of biosignatures, even chemistry that's ambiguous but suggestive, the entire field of astrobiology shifts. The conversation stops being about whether life exists elsewhere and starts being about how common it is, how diverse it can be, what forms it takes under different conditions. Titan's exotic chemistry, the hydrocarbons and nitrogen compounds and trace oxygen and water interactions, makes it a testing ground for the limits of biochemistry. Life on Earth is carbon-based, water-solvent, oxygen-breathing or oxygen-producing, depending on the organism. That's the only template we have. Titan forces us to ask whether that template is universal or just local, whether life requires water or just requires a liquid, whether it requires moderate temperatures or just requires chemical reactions to occur at some non-zero rate, whether the specific molecules we associate with life, DNA, proteins, ATP, are necessary or just what happened to work on Earth. The answers to those questions matter beyond Titan. They matter for every exoplanet survey, every search for habitable worlds around other stars. If life requires Earth-like conditions, water and oxygen and moderate temperatures, then the number of habitable planets in the galaxy is relatively small. A few % of rocky planets in the habitable zone of their stars, maybe billions total across the Milky Way, but still a minority. If life can happen in methane lakes at -179 Celsius, or in subsurface oceans on icy moons with no surface habitability, or in high-pressure hydrogen atmospheres on gas giants, then the number of habitable environments explodes. Every moon with a subsurface ocean becomes a candidate. Every cold planet with liquid hydrocarbons becomes a candidate. Every place with chemistry and energy and time becomes a candidate. The galaxy stops being mostly empty and starts being mostly full, teeming with potential habitats we haven't even thought to look for yet. That's the stakes. Not just whether Titan has life, whether life is a rare accident tied to specific conditions or a common outcome of chemistry given enough time and stability. Titan is the test case, the one place in the solar system besides Earth where the chemistry is complicated enough, the environment stable enough, and the energy sources present enough that biology might have happened independently. If it did, we're not alone. If it didn't, we learn what separates chemistry from biology, and we adjust our expectations accordingly. Either way, we have to go. We have to sample the lakes, analyze the organics, drill through the ice, measure the isotopes, map the chemistry, look for patterns. The science demands it. The questions are too fundamental to leave unanswered, and the fact that Titan also happens to be the most practical destination for long-term human presence, with an atmosphere that shields and protects, with fuel and materials in abundance, with conditions that allow surface operations without pressure suits, makes the case even stronger. We're not just exploring Titan to satisfy curiosity, we're exploring it because it's the next step, the place where science and settlement overlap, where the search for life and the search for a second home point to the same destination. Mars had its chance, the Moon had its chance. Both fell short because they couldn't deliver the one thing that matters most: protection, habitability, an environment that doesn't require you to fight every second just to stay alive. Titan delivers that, and as a bonus it might also deliver the answer to whether we're alone in the universe, or at least whether we're alone in the solar system. Because if methane lakes 886 million miles from the Sun can brew up something that qualifies as alive, then the universe is a lot more interesting than we thought. and the engineering challenge of reaching Titan stops being an obstacle and starts being an imperative. We've spent the last several chapters establishing what Titan is, what it offers, why it matters. The atmosphere that shields and protects, the hydrocarbon lakes that solve the energy problem before you even land, the exotic chemistry that might be running experiments in the origin of life while we sit here debating whether to visit. All of that is true, all of that is documented, and all of that is irrelevant if we can't figure out how to actually build something there that keeps humans alive long enough to matter. Because Titan is not a destination you visit for a weekend. It's 7 years away by current propulsion, minimum. Once you're there, you're staying. No quick abort, no emergency return flight, you're committed. And that means the infrastructure you build has to work, has to be robust, has to handle conditions so alien that most of the engineering textbooks we've written for Earth-based construction become suggestions at best and liabilities at worst. Negative 179 degrees Celsius surface temperature, an atmosphere made of nitrogen and methane, gravity 1/7 of Earth's, lakes of liquid hydrocarbons, a sky thick with organic haze. None of that is in the handbook, but here's the thing, Titan's strangeness, the same factors that make it sound impossible, are also what make it solvable. The thick atmosphere that seems like an exotic complication is actually doing half the work of keeping you alive. The low gravity that sounds like a health hazard is also what makes construction trivial compared to Earth. The methane lakes that sound dangerous are sitting there waiting to be pumped for fuel. The engineering challenges on Titan are not about fighting the environment the way you do on Mars or the Moon. They're about adapting to it, using what's there, turning the alien conditions into advantages instead of obstacles. That's the pivot. That's what makes Titan not just theoretically habitable, but practically buildable. Start with the habitats because that's where everyone lives, and if the habitats fail, nothing else matters. On Mars or the Moon, you're building bunkers. Thick walls to stop radiation, pressure vessels to hold 1 atmosphere of air against near vacuum outside, heavy structures because you're fighting a 16-to-1 pressure differential, and any failure means explosive decompression and death in seconds. Mass becomes the solution to everything. Pile more regolith on the roof, thicken the walls, go underground. Every added layer of protection is another ton of material you had to either launch from Earth or excavate locally, and either option is expensive in time, energy, and risk. Titan flips that. The outside pressure is 1.45 atmospheres. The inside pressure, what humans need to stay comfortable, is 1 atmosphere. You're not holding back vacuum. You're managing a pressure differential of less than half an atmosphere, about the difference between sea level and 5,000 feet of altitude on Earth. That's not structural stress. That's barely noticeable. It means your habitat walls don't need to be pressure vessels. They need to be insulated barriers. The structural load is almost nothing. You're not fighting to keep air in. You're fighting to keep heat in and cold out. That opens up inflatable habitats, the kind of lightweight expandable structures that have been proposed for decades, but never made sense on Mars or the Moon because the pressure differential made them too risky. On Titan, an inflatable habitat is just an insulated balloon. Fill it with warm air at 1 atmosphere, anchor it to the ground, heat the interior, and you've got livable space. The fabric doesn't need to be spacecraft-grade pressure-resistant polymer. It needs to be thermally insulating, airtight enough to prevent slow leaks, and tough enough to resist abrasion from Titan's fine-grained surface material. Those are material science problems, not structural engineering nightmares. You're talking about fabric layers, aerogel insulation, maybe a reflective coating to minimize radiative heat loss. All of it weighs a fraction of what a rigid pressure hull would weigh. The low gravity makes it even easier. A structure that would sag or collapse under its own weight on Earth stays rigid on Titan with minimal internal support. You can build large volumes with thin walls because the weight pressing down is 1/7 what it would be at home. An inflatable dome 50 meters across, tall enough to feel like you're standing in a cathedral instead of a closet, could be supported by internal air pressure and a lightweight frame. No massive girders, no thick concrete walls, just insulation, a pressure bladder, and enough heat to keep the interior above freezing. That heat is the real challenge. Titan's surface sits at negative 179 Celsius. Your habitat needs to maintain something close to 20 Celsius for human comfort, maybe 15 if everyone's willing to wear sweaters. That's a 200-degree temperature difference between inside and outside. Heat flows from hot to cold, Always, unavoidably. The only question is how fast. Your job is to slow that flow enough that the heat you're generating inside from people, from equipment, from whatever power source you're running, stays inside long enough to keep the air warm. Insulation is the answer, and Titan gives you options. Aerogel, that ultralight foam made from silica or carbon that's mostly air, has one of the lowest thermal conductivities of any material we can manufacture. A few centimeters of aerogel between your habitat's inner wall and the outside atmosphere would cut heat loss dramatically. You could manufacture it locally if you can source silica from Titan's crust, which is mostly water ice with rock mixed in. Alternatively, you use Titan's own atmosphere as insulation. Build double-walled structures with a gap between the walls, fill that gap with nitrogen from the outside air, and the gas itself acts as a thermal barrier. It's not as effective as aerogel, but it's free and it's everywhere. The power to generate that heat comes from methane, the same methane sitting in the lakes a few kilometers from wherever you decide to land. Burn methane with oxygen, and you get heat, carbon dioxide, and water vapor. The oxygen comes from splitting water, which you're sourcing either from Titan's subsurface ice or importing as a one-time payload from Earth. Once you've got an oxygen supply, the methane is functionally unlimited. Pump it from a lake, pipe it to your habitat, burn it in a controlled combustion system with heat exchangers that transfer thermal energy into your habitat's air or water-based heating loops. The technology is mature. We've been burning methane for heat and power on Earth for more than a century. The only difference on Titan is that the methane is colder when you pump it, so you need to warm it slightly before combustion to keep it liquid in your fuel lines. Minor problem. Solvable with trace heating or by running the fuel lines through the warm interior of the habitat before they reach the burner. Carbon dioxide from combustion is a waste product, but it's manageable. You can vent it into Titan's atmosphere where it disperses and eventually breaks down through photochemistry in the upper atmosphere. Or you can capture it and use it as feedstock for chemical processes, reacting it with hydrogen to produce more methane or synthesizing it into other carbon compounds you need for manufacturing. Closed-loop systems prefer the second option because it reduces waste and keeps your resource cycle tight. Open-loop systems, early colonies that haven't built out full industrial capacity yet, would just vent it. Titan's atmosphere is big enough to absorb whatever small amounts of carbon dioxide a human settlement produces without noticing. Then there's the question of how you move between habitats, how you transport people and equipment across a surface where walking is slow and ground vehicles are fighting terrain. Titan's answer is flight. Not eventually, not as a luxury. Flight is the default. The atmosphere is 1.45 times denser than Earth's at sea level. Gravity is 1/7. That combination makes lift absurdly easy to generate. A human wearing a wingsuit, a lightweight fabric rig that increases surface area and generates lift, could probably glide on Titan with minimal effort. Add a small motor, a propeller or ducted fan, and you've got powered flight. Add a little more power and you've got vertical takeoff and landing. The energy cost is negligible compared to what the same maneuver would require on Earth. Rotorcraft, quadcopters and helicopters become cargo haulers instead of experimental tech. NASA's Dragonfly mission proved the concept. A drone the size of a car, powered by a small nuclear generator, flying hundreds of kilometers across Titan's surface. Scale that up or down depending on your needs. Personal flyers for individual transport, cargo drones to move equipment between habitats, larger aircraft for bulk transport, flying at altitudes where the air is even thinner and faster. Speeds are possible without excessive drag. You're not building roads, you're not laying rail, you're building landing pads and charging stations and letting the atmosphere do the work. There's a more radical concept that keeps coming up in Titan mission proposals: airship cities, floating habitats, buoyant structures suspended in Titan's atmosphere by heated gas or vacuum chambers, drifting with the wind or propelled by engines. The idea sounds like science fiction until you run the numbers. Titan's atmosphere is dense and cold. Warm gas is less dense than cold gas. Heat a volume of nitrogen to room temperature, and it becomes buoyant in Titan's frigid air, the same way a hot air balloon rises on Earth. The buoyancy force is strong enough to lift significant weight. A habitat filled with warm, breathable air, the same air humans need to survive, would naturally float in Titan's atmosphere without requiring exotic lifting gases or complicated ballast systems. That's the elegant part. Your life support system, the warm, oxygenated air you're breathing, is also your lift mechanism. You're not adding weight to generate buoyancy. You're using what you already need. The habitat becomes a balloon, insulated to retain heat, pressurized to 1 atmosphere and buoyant by default. Anchor it to the surface when you want it stationary. Release the anchor and let it drift when you want to move. Add propulsion, small electric motors driving propellers, and you can steer it, navigate to different regions, follow seasonal weather patterns, avoid storms. The advantages are real. Floating habitats don't need ground-level infrastructure, no foundations to dig, no terrain to clear. You inflate the structure, heat it, and it rises. If you want to relocate, you don't dismantle and rebuild, you just fly to the new location. If a meteorite impact or surface hazard threatens one area, you move. The mobility makes the colony less vulnerable to localized disasters, and the altitude gives you a different perspective, a view across kilometers of landscape, a vantage point that makes surveying and exploration easier. The challenges are also real. Floating habitats are exposed to wind, and Titan has wind. Not constant, not hurricane force, but present. Measured wind speeds at the surface are typically a few meters per second, walking pace. Higher in the atmosphere, speeds increase. A floating habitat would need station-keeping systems, propulsion to counteract drift, maybe tethers to anchor it during storms. The structure would need to be robust enough to handle buffeting without tearing or losing pressure. And you'd need redundancy, multiple lift cells or compartments so a single failure doesn't send the whole thing crashing down. But none of that is unsolvable. It's engineering. Design problems with known solutions. Build in redundancy, use strong lightweight materials, synthetic fabrics reinforced with carbon fiber or Kevlar. Monitor weather, avoid high wind regions or altitudes. The technology for lighter-than-air craft exists. We've been building airships and blimps and balloons for more than 2 centuries. The principles are the same. The environment is different. Adapt the design, test it, iterate, and you've got a working system. Ground-based habitats are simpler to start with, which is why early Titan colonies would likely build on the surface near a methane lake or sea. Proximity to fuel is essential. Proximity to the subsurface water ice layer is useful for oxygen production. A site near Kraken Mare or Ligeia Mare, Titan's largest seas, offers both. The shoreline gives you access to liquid methane for fuel and chemical feedstock. The terrain is relatively flat, easier to build on than mountainous regions. And the large body of liquid moderates the local temperature slightly compared to inland areas, though at Titan's temperatures that moderation is measured in single-digit degrees. Landing is the first challenge. Titan's thick atmosphere makes atmospheric entry easier than Mars or the Moon. You've got air to brake against, air thick enough that heat shields work efficiently, and parachutes deploy reliably. Cassini's Huygens probe demonstrated that in 2005, descending through Titan's atmosphere and landing intact on the surface, with instruments still functioning. A human-rated lander would be larger, heavier, more complex, but the principles are proven. Heat shield for entry, parachutes for deceleration, thrusters for final touchdown if you want precision landing near a specific site. The dense atmosphere means you don't need as much fuel for the descent as you would on Mars. The atmosphere does most of the work. Once on the surface, the first priority is power. Nuclear is the obvious choice for a colony that can't rely on solar. Titan is 9.5 astronomical units from the Sun. Sunlight at that distance is about 1% of what Earth receives. Solar panels would produce negligible power, barely enough to trickle-charge batteries. Nuclear reactors, small modular units, like the kilopower reactors NASA has been developing, provide steady baseline power independent of sunlight or weather. A 10-kilowatt reactor, roughly the size of a trash can, could power a small habitat and basic life support. Scale up to 100 kilowatts or a megawatt, and you've got enough for industrial processes, water electrolysis, heating, manufacturing. The reactor needs cooling, which is counterintuitive on a world where the ambient temperature is negative 179 Celsius. But reactors generate heat, lots of it, and that heat has to go somewhere. On Earth, we cool reactors with water or air. On Titan, you use the atmosphere. Run coolant loops through heat exchangers exposed to the outside air. The temperature differential is enormous, 200 degrees or more between the reactor coolant and the outside environment. Heat flows out fast, efficient. The challenge is managing the coolant, making sure it doesn't freeze in the lines, which means using fluids with very low freezing points or maintaining trace heating in the system to keep everything liquid. Engineering complexity, yes, but solvable. Water is the next priority. Titan's surface is dry in the sense that there's no liquid water. It's too cold. Water ice is rock hard, thermally stable, part of the landscape. The subsurface is a different story. Drill down through the ice crust, maybe 10 to 50 meters depending on location, and you hit either more ice or possibly pockets of liquid water mixed with ammonia that lower the freezing point. Some models suggest Titan's crust is layered, with pure water ice near the surface and ammonia water slush deeper down. Either way, drilling gets you to frozen water that you can melt and purify. Melting ice requires energy, but you've got methane and a reactor. Heat water ice to 0 Celsius and it melts. Boil it to sterilize if you're worried about contamination, though Titan's surface has been frozen for so long that biological contamination is unlikely unless something survived in the subsurface ocean and got transported upward somehow. Once you've got liquid water, you electrolyze it. Run an electric current through water with dissolved salts or acids to aid conductivity, and it splits into hydrogen and oxygen. The oxygen goes into your life support system for breathing and for burning methane. The hydrogen can be vented, used as fuel for specific applications, or reacted with carbon dioxide from combustion to produce more water and methane through the Sabatier reaction, closing another loop in your resource cycle. Food production is the trickiest part of any closed-loop system because plants need light, nutrients, water, and carbon dioxide, and they produce oxygen and biomass. On Titan, you're growing food indoors under artificial light because the natural sunlight is too dim and the outside atmosphere is unbreathable. Hydroponic or aeroponic systems work, no soil required. Nutrient solutions delivered directly to plant roots. LED grow lights tuned to the specific wavelengths plants use for photosynthesis, mostly red and blue. The whole setup fits inside a pressurized greenhouse module, temperature controlled, humidity managed, carbon dioxide levels elevated above Earth normal to boost growth rates. The carbon dioxide comes from your combustion exhaust, or from the small amounts humans and equipment produce through respiration and metabolic processes. The water is recycled, collected from the air, from plant transpiration, from human waste. The oxygen plants produce goes back into the life support system. The biomass, the actual food, is harvested and eaten or processed into other forms. Potatoes, leafy greens, tomatoes, dwarf wheat, whatever crops have been optimized for space farming. Variety is limited, nutrition is adequate, and taste is secondary to survival. Later colonies with more infrastructure might support aquaculture, fish or shrimp raised in tanks, or insect farming for protein. Early colonies eat vegetables and nutrient paste and deal with it. Waste recycling completes the loop. Human waste, water, solid, everything is processed and returned to the system. Water is filtered and sterilized, multiple stages to ensure nothing pathogenic survives. Solid waste is composted or incinerated depending on the system design. Composting produces useful soil additives for plant growth if you're running a soil-based system instead of hydroponics. Incineration reduces waste to ash and gases. The gases are scrubbed and vented or captured. The ash is either stored or used in manufacturing processes that can incorporate inert filler material. None of it is wasted. None of it can be wasted. Resupply from Earth takes 7 years. Once you're on Titan, every atom you brought with you or extracted locally has to cycle through the system indefinitely. Waste is just a resource you haven't figured out how to use yet. Manufacturing capability grows over time. Early colonies import most of their equipment and tools from Earth. Later colonies build more locally. Plastics and polymers from hydrocarbon feedstocks. Simple metal parts cast or machined from imported raw materials. Eventually, if the colony survives and grows, local mining and refining. Titan's crust is water ice and rock, silicates and possibly trace metals. Not richer deposits like you'd find on Earth or certain asteroids, but workable if you're willing to process large volumes of material to extract what you need. The energy cost is high, but energy is cheap on Titan once you've got methane flowing and reactors running. 3D printing becomes essential. Additive manufacturing, building parts layer by layer from raw material, reduces the need for complex machining and lets you produce custom components on demand. Print replacement parts for equipment that breaks. Print structural elements for expanding habitats. Print tools, containers, fittings, anything that can be made from plastic or metal powder. The printers themselves are imported, but the feedstock can be local hydrocarbons or recycled material from damaged equipment. It's not self-sufficiency, not yet, but it's a step toward reducing dependence on Earth. Robert Zubrin, the aerospace engineer who's been advocating for Mars colonization for decades, called Titan the most hospitable extraterrestrial world within our solar system for human colonization. Not Mars, Titan. That's a hell of a statement coming from someone who built his career arguing that Mars was the obvious next step. But Zubrin is an engineer, and engineers follow the numbers. Titan's atmosphere, its resource base, its low gravity, the way all of those factors combine to make construction and operation easier than Mars, pushed him toward a conclusion that contradicts 50 years of space exploration priorities. The closest world isn't always the best world. The most familiar world isn't always the most habitable. Titan works because the engineering advantages outweigh the distance penalty. You pay the cost of getting there once. 7 years in transit, one way. After that, you're living in an environment that doesn't fight you every second of every day. The psychological side matters too, though it's harder to quantify. Living on Titan isn't like living in a bunker on Mars or underground on the Moon. You've got a sky, not black, orange, hazy, thick. You see clouds, you see weather developing, you hear wind through your suit when you're outside. The atmosphere is active, dynamic, moving. It feels like a place where things happen, where the environment is alive in the geological sense. That's not nothing. Humans respond to environments. We evolved under an atmosphere, under weather, surrounded by motion and change. A sky that's black and unchanging, a horizon that's static and lifeless, that wears on people. Submariners, Antarctic winter-over crews, anyone who's spent months in confined, unchanging environments, they report psychological strain, depression, interpersonal conflict. Titan's atmosphere, strange as it is, provides variability. The weather changes. The light shifts as Titan orbits Saturn and Saturn orbits the Sun. Seasonal cycles play out over years, but they play out. You're not frozen in geological time. You're part of a system that's running, that has rhythms, that responds to forces beyond human control. That connection to a dynamic environment, even an alien one, might be what keeps a colony psychologically stable over the decades it would take to establish a permanent presence. The engineering marvel isn't any single technology, it's the integration. The way Titan's conditions, all of them, combine to allow systems that wouldn't work anywhere else. Inflatable habitats because the pressure differential is manageable. Flight as default transport because the atmosphere is dense and gravity is low. Methane as unlimited fuel because it's sitting in lakes on the surface. Local manufacturing from hydrocarbon feedstocks because the chemistry is there. Closed-loop life support because you've got the energy to run it and the raw materials to maintain it. Every piece fits, every system supports the others. Build one habitat and you've proven the concept. Build 10 and you've got a settlement. Build 100 and you've got a city, spread across Titan's surface or floating in its atmosphere, powered by local resources, sustained by local chemistry, independent of Earth except for the occasional shipment of things Titan doesn't have. That independence is the endgame, not a research outpost that lives or dies based on funding from Earth governments, a self-sustaining colony that survives because it works, because the environment provides what it needs, because the people there can build and grow and expand without waiting for permission or resupply. Titan makes that possible in a way Mars and the Moon don't. The resources are there, the protection is there, the engineering path is clear, it's not easy. Nothing about space colonization is easy. But easy and possible are different categories, and Titan sits firmly in the possible column once you account for the distance and commit to solving the problems that distance creates. 7 years to get there. Decades to build out infrastructure. Generations to reach true independence. That's the timeline, that's the commitment. And if you're serious about humanity becoming a multiplanetary species, about creating a backup for civilization that survives even if Earth doesn't, then Titan is where that backup gets built. Not as a compromise, not as a fallback, as the destination that delivers what everywhere else promises and fails to provide: habitability, resources, a future that doesn't require fighting the environment every day just to survive. That's the engineering marvel, not what we build on Titan, that we can build on Titan at all. That 886 million miles from the Sun, in an environment so alien it breaks every assumption we've carried about what a habitable world looks like. The numbers work, the chemistry works, the physics works, and the only thing stopping us from going is the decision to start. We've established the engineering, we've walked through the chemistry, the atmosphere, the fuel sitting in lakes waiting to be pumped, the habitats that don't require pressure suits, the flight capability that turns transport into a solved problem. We've shown that Titan works, that the numbers add up, that the technology exists or can be built with what we already know. The case is closed on the practical side. Titan is habitable in ways Mars and the Moon aren't. Titan is resource-rich in ways no other destination can match. Titan offers protection, energy, materials, and an environment that doesn't spend every second trying to kill you. All of that is documented, all of that is true, and yet the conversation keeps circling back to Mars. Mars gets the missions, Mars gets the funding, Mars gets the billionaires with rocket companies, and the NASA roadmaps, and the international partnerships, and the public enthusiasm. SpaceX is building Starship to go to Mars. NASA's Artemis program is positioning the Moon as a stepping stone to Mars. China is planning crewed Mars missions. Everyone is still pointing at the red planet like it's the inevitable next chapter in human history. Like proximity equals destiny. Like the fact that we can see Mars with the naked eye from Earth means that's where we're supposed to go. And Titan, 886 million miles out, sits there in the data, in the Cassini images, in the astrobiological models and engineering proposals, largely ignored by everyone except the scientists who've actually looked at what it offers. That gap between what the data says and where the momentum is tells you something uncomfortable about how humans make decisions. We don't follow the evidence, we follow the story, and the story we've been telling ourselves for a century is that Mars is next. That narrative has so much inertia, so much cultural weight, so many books and movies and mission patches and rover names attached to it that shifting the target feels like admitting we were wrong, like throwing away 100 years of work, like abandoning the dream. Except the dream was always about survival, about expansion, about making sure humanity doesn't stay confined to one fragile planet where a single asteroid impact or supervolcano or runaway climate shift or nuclear war could erase everything we've ever built. The dream was never specifically about Mars. Mars just happened to be the nearest thing that looked vaguely planet-like, and in the absence of better options, we convinced ourselves it was the answer. But better options exist now. We have the data. We've mapped Titan. We've measured its atmosphere, sampled its chemistry, confirmed its lakes and seas and weather and organic inventory. We know what's there. And what's there is a world that solves problems Mars creates. The shift required isn't technical, it's psychological. It's admitting that nearness isn't the same as suitability, that familiarity isn't the same as habitability. That the place we've been pointing at for generations might not be the place that gives us the future we actually need. That's a hard shift. It requires letting go of assumptions that have guided space exploration, since Wernher von Braun was sketching Mars rockets in the 1950s. It requires accepting that the easy answer, the close answer, the answer that fits our intuitions about how colonization should work is the wrong answer. And it requires committing to a destination so far away, so cold, so strange, that it forces us to rethink what a second home even looks like. Titan is not a backup Earth. It will never be a backup Earth. The surface temperature is negative 179 Celsius. The atmosphere is nitrogen and methane. The rain is liquid hydrocarbons. The lakes are flammable if you add oxygen. The gravity is 1/7 Earth normal. The sky is orange. The sun is a dim point of light barely brighter than the full moon seen from Earth, and the seasons last 7.5 years each. You're not transplanting human civilization to a place that looks like home. You're adapting human civilization to a place that works despite looking nothing like home. That's the paradigm shift. That's what separates Titan from every other destination we've considered. Mars let us pretend we could colonize the solar system without changing much. Close enough that resupply is feasible. Similar enough in day length and gravity that the adjustment seemed manageable. Red dirt and dry riverbeds and polar ice caps that looked almost familiar if you squinted. We told ourselves Mars was a practice run, a place to learn the basics before tackling harder targets. And maybe that's true in a limited sense. Maybe Mars teaches us how to live off-world in the same way that early Antarctic expeditions taught us how to survive in extreme environments. But Antarctica didn't become a self-sustaining civilization. It became a research outpost, staffed seasonally, dependent on external supply lines, abandoned the moment conditions deteriorate or funding dries up. Mars, with its lack of atmosphere and magnetic field, with its radiation and toxic soil and resource scarcity, is heading toward the same fate. A valuable testing ground, a place to visit and study, but not a place to build a future that survives independently. Titan forces a different model. You can't treat Titan as a short-term project. The travel time alone, 7 years minimum with current propulsion, turns every mission into a multi-decade commitment. You're not sending people for a 2-year surface stay and then bringing them home. You're sending them knowing they might never come back, that the colony they're building is the goal, not the research they're conducting, that success looks like self-sufficiency, not data return. The psychology of that mission is fundamentally different from anything we've attempted. Apollo was a sprint. The International Space Station is a marathon. Titan is a one-way emigration with no guarantee of survival and no realistic prospect of rescue if things go wrong. You're asking people to leave Earth, leave everyone they know, spend the better part of a decade in transit, and land on a moon so alien that every assumption about daily life has to be rebuilt from scratch. That's not exploration. That's colonization in the oldest, most literal sense. You're going somewhere new with the intent to stay, to build, to make it work because there's no other option. And the people who go will have to believe in it. Not just tolerate it, not just accept it as the least bad option, but genuinely believe that Titan offers something Mars doesn't. A future that's worth the distance, a world that's worth the strangeness, an environment that protects and provides instead of fighting and draining. That belief is the foundation. Without it, the colony fails. With it, you get a population willing to endure the isolation, the cold, the years of construction and iteration and failure, because they understand what they're building. A civilization that doesn't depend on Earth. A society that survives on its own terms, using local resources, solving local problems, evolving into something that fits Titan, instead of trying to force Titan to fit humanity. Robert Zubrin, who spent decades arguing that Mars was the obvious next step, called Titan the most hospitable extraterrestrial world within our solar system for human colonization. That statement, coming from someone who built his career on Mars advocacy, is worth sitting with. Zubrin is not sentimental. He's an engineer, he follows the numbers, and the numbers led him to Titan despite the distance, despite the cold, despite the fact that it contradicts everything he'd argued before. The most hospitable world. Not the closest, not the most familiar, the one where the environment works with you instead of against you, where the atmosphere shields instead of exposing, where the resource base supports expansion instead of limiting it, where the engineering challenges are solvable without requiring magic or wishful thinking. Ralph Lorenz, another researcher who spent years studying Titan, called it a mega factory of organic chemicals. That phrasing captures something essential. Titan isn't static. It's not a frozen relic. It's an active system, churning out complex molecules, cycling materials between the surface and the atmosphere, running experiments in chemistry that have been going on for billions of years. That activity is the baseline. That's what you're landing in. Not a dead world that needs to be revived, a living world, geologically and chemically, that's already doing most of the work required to support a technological civilization. The factory is running. You just have to plug into it. The long-term vision isn't a single base clinging to the shoreline of a methane sea. It's multiple settlements spread across Titan's surface and possibly floating in its atmosphere, connected by air transport, trading materials and expertise, specializing in different industries. One settlement focused on hydrocarbon extraction and fuel production, another on agriculture, growing food in pressurized greenhouses under artificial light, another on manufacturing, synthesizing plastics and polymers and structural materials from local feedstocks, another on research studying Titan's chemistry and biology if it exists, mapping the subsurface ocean, drilling through the ice to sample what's below. Each settlement self-sufficient in the basics, heat and power and life support, but interdependent for the higher order functions that make a society more than a survival outpost. That interdependence is what makes it a civilization instead of a collection of isolated bunkers. You're not replicating Earth's nation-states, drawing borders, competing for resources. You're building a network, distributed across a moon-sized territory, linked by communication and trade, and the shared understanding that everyone's survival depends on the system working. If one settlement loses power, another can send fuel and equipment. If one settlement's agriculture fails, another can ship food. If one settlement discovers a breakthrough in material science or water extraction, or any of the 1,000 technical problems that a Titan colony would face, that knowledge propagates across the network immediately, because hoarding it helps no one. The distance from Earth enforces cooperation. There's no external authority to arbitrate disputes. There's no resupply ship arriving if you screw up. You either work together or you die separately. That's the forcing function that turns a colony into a civilization. The timeline is generational. First generation builds the infrastructure, proves the systems, survives long enough to establish a foothold. Second generation expands, adds capacity, diversifies the industrial base, starts producing more locally and importing less from Earth. Third generation is born on Titan, grows up in low gravity under an orange sky, speaks English or Mandarin or Spanish, with an accent shaped by wearing breathing masks outdoors and living in enclosed habitats. Fourth generation barely remembers Earth except as a historical abstraction, a place their great-grandparents came from, a planet that's 7 years away by ship and increasingly irrelevant to daily life. By the fifth generation, you've got a culture that's Titanian, not Earthling. People who think in terms of methane fuel cycles and seasonal weather patterns that last a decade. People who look at images of Earth and see a world that's too bright, too warm, too chaotic. Home is the orange haze and the liquid hydrocarbon seas and the low gravity that makes flight trivial. Earth is somewhere else. Someone else's problem. That divergence is inevitable. You can't keep a colony culturally synchronized with Earth across light-hour communication delays and 7-year travel times. The cultures will drift. The priorities will shift. The colony will develop its own identity, its own values, its own way of doing things that makes sense in context and looks alien from the outside. That's not a failure, that's success. It means the colony has stopped being an extension of Earth and started being its own thing, sustainable, independent, capable of surviving, even if contact with Earth is severed permanently. The goal was never to build a copy of Earth on Titan. The goal was to build something that survives when Earth can't. And survival requires adaptation, requires change, requires letting go of the assumption that human civilization has to look like the version we built on one specific planet, under one specific set of conditions. The propulsion problem is the gatekeeper. Current chemical rockets can get you to Titan, but the travel time is brutal and the mass fractions are prohibitive. You're spending most of your fuel just accelerating the fuel you need for the rest of the trip. The rocket equation doesn't care about your destination's advantages. It cares about delta V, and Titan is expensive in delta V. Nuclear propulsion changes the math. Ion drives, nuclear thermal rockets, maybe nuclear pulse propulsion, if anyone ever gets comfortable with the idea. These technologies provide higher exhaust velocities, better specific impulse, which translates to lower fuel mass for the same mission. A nuclear electric ion drive could cut the travel time to Titan from 7 years to 3 or 4, depending on the power levels and how much mass you're willing to push. A nuclear thermal rocket using hydrogen propellant could do even better, though the engineering challenges are significant, and the political hurdles around launching fissile material into space are non-trivial. But those challenges are solvable. We've built nuclear reactors for submarines that operate for decades without refueling. We've tested nuclear rocket engines in the 1960s and 70s, programs like NERVA that proved the concept before funding dried up. The technology exists. It's not exotic, it's just expensive and politically complicated, which are barriers that disappear the moment the mission becomes a priority. If the goal is Titan, if the decision is made that Titan is where humanity's second home gets built, then the propulsion development happens, the reactors get built, the ion drives get scaled up, the mission architectures get optimized, and the travel time drops from 7 years to something closer to 3, which is still long but manageable, within the range of what human psychology can endure with proper crew selection and habitat design and mission planning. 3 years in transit. Arrive at Titan. Land near Ligeia Mare or Krakenmare, the major seas that offer proximity to fuel and relatively flat terrain for construction. Deploy the initial habitat modules, inflatable structures pre-packed on the lander, expanded and pressurized once on the surface. Drill for water ice, start electrolysis. Produce oxygen for life support and for burning methane. Pump methane from the sea, run it through combustion systems for heat and power, supplement with nuclear reactors for baseline load. Set up the greenhouse modules, start growing food under LED lights, cycle carbon dioxide from combustion exhaust into plant growth. establish communication with Earth, hour-plus light delay each way, enough to send data and receive updates, but not enough for real-time conversation. Expand the habitat as more equipment arrives on follow-up missions. Build out the infrastructure, storage tanks for fuel, landing pads for resupply, eventually fabrication facilities for producing parts locally from hydrocarbon feedstocks. Survive the first year, then the second, then the 10th. By 20 years in, you've got a settlement. By 50, a city. By a century, a civilization that's forgotten what it was like to live under Earth's sky. That's the vision. That's what Titan offers. Not a research base that closes down when the funding runs out. Not a prestige project that gets mothballed after the first crew comes home. A permanent expansion of human presence into the outer solar system, built on a foundation that's sustainable because the environment provides what the colony needs without constant external input. Mars can't offer that. The resources aren't there. The protection isn't there. The atmosphere that makes everything easier doesn't exist. The Moon can't offer it either. No air, no resources beyond water, ice and regolith, no baseline environment that reduces the cost of staying alive. Titan is the only place beyond Earth where the equation balances, where the distance is the price and the habitability is what you get for paying it. The philosophical shift is accepting that the future doesn't have to look like the past, that the next step in human expansion isn't a shorter version of the last step, that going farther, to a place that's stranger and colder and more alien than anything we've imagined, might be the path that actually works. We've spent 100 years assuming that space colonization would follow the pattern of terrestrial colonization, explorers finding new lands that resembled the old ones, settling in, building copies of the societies they left behind. That worked on Earth because the new lands had air and water and temperatures that humans could survive in. It doesn't work in space because nowhere else in the solar system looks like Earth, except in the most superficial ways. Mars looks like desert. Titan looks like an industrial accident. Neither one is home, but one of them offers the tools to build a new version of home that fits the local conditions. The other doesn't. The bias toward Mars is understandable. It's human nature to prefer the familiar, to choose the option that requires the least adjustment, to go for the nearby target instead of the distant one. But human nature also includes adaptability, curiosity, the willingness to take risks for long-term gain. The same species that crossed oceans in wooden boats and settled continents on foot, and built cities in deserts and jungles and tundra, can absolutely handle Titan. The adjustment is bigger, the challenge is harder, but the reward is a world that doesn't just tolerate human presence but supports it. That provides energy, materials, protection, and room to grow. That offers a genuine second chance, a backup that survives even if Earth becomes uninhabitable. The decision to go to Titan instead of Mars is a decision about what kind of future we're building. Mars is the conservative choice, the incremental step, the option that minimizes short-term risk and maximizes short-term return. It's also the option that leaves humanity stuck in the inner solar system, dependent on Earth, vulnerable to the same existential risks that make colonization necessary in the first place. Titan is the radical choice, the leap that requires faith in our ability to adapt and engineer and endure. It's also the option that breaks the dependency, that establishes a foothold so far from Earth and so self-sufficient that it survives independently. That's the future worth reaching for, not a Mars base that needs constant resupply, a Titanian civilization that grows on its own, expands on its own, evolves on its own, becomes something new. The clock is running. Earth's population is pushing 8 billion. Climate change is accelerating. Resource depletion is measurable. Political instability is rising. Nuclear arsenals still exist. Asteroid impacts are low probability but non-zero. Supervolcanoes sit dormant under Yellowstone and other sites, waiting for the pressure to build. Any one of those risks, or a combination, could reduce Earth's carrying capacity or wipe out large portions of human civilization. The backup plan can't be theoretical. It can't be decades away, perpetually postponed while we argue about funding and mission architecture and whether Mars or the Moon makes more sense as a stepping stone. The backup plan needs to be built, now, this century, and the place to build it, the place where the engineering works and the resources exist, and the environment provides a foundation for long-term survival, is Titan. We've spent enough time looking at Mars and pretending the math adds up. It doesn't. We've spent enough time staring at the Moon and convincing ourselves proximity equals practicality. It doesn't. We've spent a century building momentum toward destinations that offer survival at best and extinction by slow attrition at worst. Titan offers something different, a world that's strange enough to force adaptation and rich enough to reward it. A world 886 million miles away that paradoxically offers more habitability than the world's 55 million miles away. A world with an atmosphere, with lakes, with weather, with chemistry running wild, with everything required to build a future that doesn't end the moment Earth stumbles. The new cosmic compass doesn't point toward the nearest rock with a name. It points toward the world that works, the one where the numbers add up, the one where the resource base supports growth instead of limiting it, the one where the environment shields instead of exposes, provides instead of depletes, enables instead of restricts. That world is Titan. The data says so, the engineering says so, the chemistry says so. The only thing missing is the decision to stop pointing at Mars and start building the ships that go farther, to stop optimizing for proximity and start optimizing for survival, to stop asking whether we can reach Titan and start asking what we'll build when we get there. Humanity's destiny isn't written by geography, it's written by choices. We chose to leave Africa, we chose to cross oceans, we chose to reach the moon. Every one of those choices looked impossible until someone decided it wasn't. Titan is the next choice, the one that redefines what we mean by habitable, by reachable, by home, the one that turns 886 million miles from an obstacle into a filter, separating the colonies that survive from the outposts that don't. The one that proves we're not limited to the inner solar system, not confined to worlds that look like Earth, not stuck repeating the same mistakes until the environment or our own limitations catch up with us. The compass is pointing. The destination is clear. The only question left is whether we're willing to follow it. We spent a century staring at the wrong horizon. Mars glowed red in our telescopes, and we called it destiny because it was close, because we could see it without instruments, because proximity felt like permission. The moon hung overhead every night, and we convinced ourselves that nearness meant suitability, that the first step off Earth would naturally be the easiest one. We built our dreams on geography, on distance measurements, on the comfortable assumption that the next home would look enough like the last one that the transition would be manageable. We were wrong about all of it. Titan sits 886 million miles away, cold enough to turn water into bedrock, strange enough that methane falls as rain and pools in seas larger than the ones we grew up beside. It should have been dismissed. It should have stayed a footnote in planetary science textbooks, a curiosity for specialists, too far and too alien to matter. But the data didn't care what we assumed. The measurements didn't care what felt intuitive. And when the numbers came back, when Cassini mapped the lakes and Webb confirmed the chemistry and the models showed what an atmosphere that thick actually provides, the conclusion was inescapable. The world we've been ignoring is the world that works. Not because it's easy, not because it resembles home, because it offers what Mars and the Moon never could. Protection without needing to be built, energy without needing to be rationed, an environment that shields and moderates and cycles materials through weather patterns we recognize even if the chemistry is alien. A baseline that doesn't require you to fight for every breath, every degree of warmth, every hour spent outside a bunker. Titan is the answer we didn't want because it forced us to admit that the future doesn't follow our intuitions, that survival requires going farther, adapting harder, building something that doesn't look like a copy of Earth but functions anyway, that the compass pointing toward humanity's second home isn't aimed at the nearest dot of light, but at the one world in the solar system where the atmosphere does half the work of keeping you alive. The question was never whether Titan is reachable, it's whether we're willing to reach for it. Before we build outward, we must demand the science, safeguards, and shared institutions worthy of worlds that cannot speak for themselves.